Hello there and welcome to Physics with William, where curiosity settles down for the evening and the universe is allowed to explain itself at a comfortable pace. Tonight, we're going to spend a little while with a question that sounds simple at first, almost like the kind of thing a child might ask while tapping a spoon on the table. But the more you think about it, the stranger it becomes. If electrons repel each other, why does anything stay together? Why does a table remain a table? Why does the air not burst apart? Why do stones, books, oceans, trees, cups of tea and sleepy people under blankets not simply fly away in all directions as if the whole world were made of tiny magnets turned the wrong way around? It is a wonderfully odd thing to wonder about, because everything around you is made of atoms, and every atom contains electrons. Electrons carry the same kind of electric charge as one another, and particles with the same kind of electric charge push away from each other. That is one of the first rules we learn when we begin exploring electricity. Like charges repel, unlike charges attract. It sounds tidy enough. It sounds dependable. It sounds like the kind of rule that should make the universe easy to predict. And yet here we are, sitting inside a universe that appears to have taken that simple rule and built flowers, mountains, clouds, wooden floors, eyelashes, planets, spoons, and the occasional very determined house cat. So there is the puzzle. If the tiny negatively charged electrons in matter do not want to be near other electrons, then why does matter not tear itself apart? Why is your chair quietly holding you up, instead of expanding into a mist of irritated particles? Why does the floor remain under your feet? Why can you press your hand against a wall and feel resistance, rather than passing through it, or causing it to explode in a very inconvenient cloud of physics? The answer is not that electrons secretly like each other. They do not. At least not in the simple electric sense. The answer is more interesting than that. Matter stays together because the universe is not governed by one rule acting alone. It is governed by balances, layers, restrictions, attractions, pressures, and patterns. Repulsion is real, but it is not the whole story. Before we go further, I would love to ask you something small and personal, because physics is always a little warmer when we remember that it is happening right where we are. Where are you listening from tonight, and what ordinary object is nearest to you right now? Maybe it is a pillow, a phone, a mug, a blanket, a window, a desk, or your own resting hand. Whatever it is quietly performing a remarkable trick. It is holding itself together. It is made of charged particles, many of which repel each other, and yet it remains calm. It does not announce its achievement. It simply sits there, looking ordinary, while the laws of nature work tirelessly beneath its surface. That nearby object is not just a thing, it is a truce. A peaceful arrangement between forces that could, under different conditions, be dramatic enough to light stars or split atoms. If you find this sort of quiet journey through science soothing, or if it helps make the strange machinery of the universe feel a little more familiar before sleep, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this small corner of calm physics reach other people who might enjoy drifting off, while learning why reality is not as solid, simple, or obvious as it first appears. And if tonight you do fall asleep before we reach the end, that is perfectly alright. The electrons will still be here in the morning, still repelling each other, still cooperating just enough to make breakfast possible. Let us begin with the feeling of solid things. Place your hand on a table, or imagine doing so. It feels firm. It seems as though your hand touches the table because the atoms in your skin meet the atoms in the wood, or metal, or plastic. But that everyday feeling of contact is already a little misleading. At the smaller scale, your hand does not truly touch the table in the way two soft pieces of clay might press into one another. What you feel as touch is mostly the resistance between electrons. The electrons in the outer regions of the atoms in your hand approach the electrons in the outer regions of the atoms in the table, and because these electrons repel, your hand is pushed back. That push is interpreted by nerves in your skin, sent to your brain, and your brain says, quite sensibly, there is a table here. This means the very solidity of the world is in part a kind of polite refusal. The table refuses to let your hand pass through it. Your hand refuses to merge with the table. The electrons in both objects are not eager to share the same space, and so a boundary appears. It is not a boundary drawn with ink. It is a boundary made of forces and quantum rules. The result is the everyday miracle of surfaces. A plate can rest on a shelf. Your feet can stand on the ground. A book can sit beside a lamp. None of this feels mysterious because it happens constantly, but underneath it is a busy world of charged particles negotiating distance. Now, it might sound as though this only deepens the problem. If electron repulsion is what makes matter feel solid, then why does that repulsion not keep pushing things apart forever? If every electron pushes every other electron away, why does a lump of matter not spread outward until it becomes thinner and thinner, like steam escaping from a kettle? The reason is that electrons are not floating around by themselves in empty space. They are part of atoms, and atoms have another major ingredient. At the centre of each atom is a nucleus, and that nucleus contains positively charged protons. Electrons are negatively charged, and protons are positively charged, so electrons are attracted toward the nucleus. There is repulsion between electrons, yes, but there is also attraction between electrons and nuclei. Matter survives because these influences do not simply cancel in a dull way, they arrange themselves. An atom is not like a tiny solar system with electrons calmly orbiting a nucleus, as planets orbit a sun, even though that picture is still common because it is easy to imagine. The real atom is stranger. Electrons behave according to quantum mechanics, which means they do not have little tracks like miniature train lines. They occupy regions, patterns, and allowed states around the nucleus. They are constrained not only by electric attraction and repulsion, but also by rules about what kinds of arrangements are possible in the first place. These rules are not optional. Electrons cannot all pile into the lowest and most convenient position. They cannot simply collapse into the nucleus. They cannot all crowd into the same exact condition. The universe has very strict rules about how electrons may exist in atoms, and those rules are one of the great reasons matter has structure. This is where the story becomes richer than the simple phrase like charges repel. That phrase is true, but it is only the doorway. Once we step through, we find that electrons are not little beads bouncing around randomly. They are quantum objects. They are described by probabilities, by allowed energies, by states that fill in particular ways. The repulsion between electrons matters very much, but it is not free to do anything it wants. It is guided and limited by the architecture of atoms. It affects how electrons arrange themselves, how atoms behave, how chemical bonds form, and how materials resist compression. But it does not cause everything to explode, because explosion is not the natural result of repulsion alone. Explosion requires a sudden release of stored energy, a pathway for matter to rearrange violently, and conditions that allow forces to run away faster than other forces can contain them. Ordinary matter is not usually in that state. It is already settled into arrangements where attraction, repulsion, and quantum rules have found workable balance. Think of a crowded room, but a calm one. No one wants to stand exactly on top of anyone else. People keep a little space around themselves. If someone moves too close, there is a gentle shift, a step aside, a murmur of adjustment. But the room does not explode simply because people prefer personal space. The walls, the furniture, the exits, the purpose of the gathering, and the behavior of the people all shape the arrangement. In matter, electron repulsion is a bit like that preference for personal space, except far more fundamental. It helps determine how close atoms can get. It helps make matter occupy volume. It helps create resistance when you squeeze something, but it operates within a larger setting, with nuclei attracting electrons, atoms bonding with other atoms, and quantum mechanics deciding which arrangements are stable. There is also a deeper point hiding here. When we say everything is made of atoms, we often imagine atoms as tiny hard grains like invisible sand. But atoms are mostly space in the ordinary visual sense. Their nuclei are incredibly small compared with the spread of their electrons. If atoms were just empty space with tiny centres, you might wonder why objects are not ghost-like. Why does matter feel dense and firm? The answer again returns to electrons and their rules. The electron regions around atoms occupy space in a quantum way. They resist being squeezed into the same states. They repel other electrons. They form shells and bonds and patterns. The world feels solid not because atoms are tiny billiard balls, but because electromagnetic forces and quantum restrictions give matter shape and stiffness. At this point, the question becomes less like, why does matter not explode? And more like, how does matter ever manage to be so stable? After all, there are forces pulling and pushing everywhere. The nucleus pulls on electrons. Electrons push on electrons. Nuclei push on other nuclei when they get close, because protons inside them are positively charged. Atoms attract each other in some ways and resist each other in others. Molecules form when electron arrangements allow atoms to lower their energy by sharing or transferring electrons, though the word sharing in chemistry is gentler than the actual quantum reality. Solids form when many atoms settle into repeated patterns or tangled structures where attractions hold them together and repulsions keep them from collapsing into one point. Your body exists because molecules are stable enough to hold shape but flexible enough to change. A star shines because matter under extreme pressure finds a very different kind of balance. A white dwarf star, one of the dense remnants left after certain stars die, is held up in part by electron behaviour under astonishing compression. Even there, electrons resist being squeezed too much, and that resistance can support something with the mass of a star. So electrons are not a problem the universe must overcome, they are part of the solution. Their repulsion is not a flaw in matter, it is one of the reasons matter has size. If electrons did not repel each other, if they did not obey quantum rules, if they did not resist certain kinds of crowding, then matter would not simply become more peaceful. It would lose the structures that make chemistry and ordinary objects possible. The same push that prevents your hand from passing through a table also helps atoms arrange into molecules. The same resistance that stops matter from collapsing contributes to the stiffness of materials. Repulsion is not destruction by default. In the right balance, repulsion is architecture. This is a useful idea beyond physics too, though we will keep our feet in science. Stability is not always the absence of tension. Often stability is the result of tensions arranged well. A bridge stands because forces oppose and support each other. A tent keeps its shape because fabric is pulled and poles push back. Your body remains upright because bones, muscles, tendons and gravity are all involved in a constant negotiation. Matter is similar. It is not calm because nothing is happening. It is calm because a great deal is happening in a balanced way. Beneath the still surface of a stone, electrons are not sleeping. They are part of a structured quantum system. Beneath the quiet surface of a glass of water, molecules are jostling, attracting, repelling, rotating, and forming temporary arrangements. Beneath your skin, charges and chemical bonds are endlessly at work. The world is quiet only from far enough away. We should also be careful with the word explode. In everyday language, explode means something bursts apart quickly and violently. In physics, something like that usually happens when a system has stored energy that can be released very fast. A firework explodes because chemical reactions produce hot gases quickly, and pressure builds until material is forced outward. A bomb releases energy through rapid chemical or nuclear changes. A star can explode when its internal balance fails catastrophically. Electron repulsion alone does not guarantee such an event. In ordinary matter, the electrons and nuclei have already settled into low-energy arrangements. They are not like a spring compressed beyond its limit waiting for a touch. They are more like a well-built arrangement of springs, weights and supports that maintains its form because every part has found a role. If you try to force matter into a smaller space, then electron repulsion and quantum effects become more obvious. Compress a gas, and pressure rises. Push solids together, and they resist. At extreme pressures, atoms change their arrangements. Electrons may be forced into new states. Materials can become metallic, crystalline, fluid, or something much stranger. Inside planets, matter is crushed into forms we do not meet at the surface. In laboratories, scientists use enormous pressures to study how atoms behave when squeezed. But even then, the result is not usually everything exploding outward. It depends on the balance of pressure, temperature, energy, structure, and whether the system has a way to release energy suddenly. Physics is rarely one rule shouting alone. It is more often a conversation between rules. The central story we will follow is therefore not that electrons repel each other, and somehow the universe ignores it. The universe takes that repulsion seriously. It builds with it. The push between electrons helps define the boundaries of atoms, the shapes of molecules, the hardness of solids, the pressure of gases, the behavior of metals, the structure of crystals, the chemistry of life, and the strange matter inside stars. It is present when you tap your finger on a wooden desk. It is present when a rubber ball bounces. It is present when two magnets resist being pushed together in the wrong orientation, though magnetism brings its own related story. It is present when a balloon holds air, when a wall supports a roof, and when your pillow holds its soft shape beneath your head. And yet, this repulsion is only one part of a larger electromagnetic world. Electrons repel electrons, but electrons attract nuclei. Atoms may be neutral overall because their negative electrons balance the positive charge of their nuclei. Neutral atoms can still attract one another through subtle shifts in their electron clouds. Molecules can form because electron arrangements around multiple nuclei can be more stable than separate atoms. Solids can persist because many atoms can settle into patterns where each atom is held near others but not allowed to collapse into them. The world does not explode because matter is not merely a crowd of mutually repelling electrons. It is a layered system of charged particles, quantum rules, and energy-seeking stable arrangements. There is something comforting about that. The ordinary things around you are not ordinary because they are simple. They are ordinary because the universe is extraordinarily good at finding patterns that last. A wooden table is temporary on cosmic timescales, of course. A mountain erodes, a star burns out, a human body changes from moment to moment. But for the purposes of an evening, a cup remains a cup. A blanket remains a blanket. A book remains a book. Their atoms hold together because the laws of physics allow stable structures to exist between collapse and explosion. Too much attraction without resistance would make matter fall inward. Too much repulsion without attraction would make it fly apart. The familiar world lives between those extremes. As we move deeper into this question, we will begin by slowing down around electric charge itself. It is easy to say positive and negative, attract and repel, but those simple words carry a great deal of meaning. We will look at what it means for particles to push or pull through empty space, how electrons came to be understood, and why the same force that can make your hair stand up after rubbing a balloon can also help hold atoms and molecules in place. From there we can step into the atom, not as a tiny mechanical toy, but as a quantum structure where electrons arrange themselves in ways that are strange, strict, and surprisingly creative. The important thing for now is to let the central mystery remain clear. Electrons do repel each other. That part is true, but repulsion does not mean chaos must win. In the quiet depths of matter, repulsion is balanced by attraction, shaped by quantum rules, and turned into the very firmness of the world resting gently around you. There is a tiny push hidden inside almost everything you have ever touched. It is there in the smooth side of a drinking glass, in the fibres of a blanket, in the cool metal of a spoon, in the skin of your hand, in the floor beneath you, and in the quiet air moving gently through the room. It is not a push you can see directly. and most of the time it does not announce itself. It does not rumble like thunder or glow like a flame. It simply works, patiently and constantly, shaping matter from within. This tiny push is electric charge. Electric charge is one of those ideas that seems familiar because we meet its effects in ordinary life. We notice static electricity when a sweater crackles in the dark, or when a balloon rubbed against hair makes the hair rise up in a rather undignified halo. We see lightning split the sky during a storm. We plug in lamps, charge phones, and live among wires that quietly carry electrical energy through walls. So electricity can feel modern, practical and domestic, something that belongs to sockets, batteries, and machines. But electric charge is much older and deeper than any technology. It is not something humans invented. It is one of the basic features of matter itself. Long before the first battery, long before the first metal wire, long before anyone had a word for electron, charge was already helping atoms form, helping molecules hold their shapes, and helping the material world resist collapse. When we say that an electron has electric charge, we are saying that it has a property that makes it respond to other charged things. A charged particle is not just a tiny speck sitting alone. It carries with it the ability to push or pull on other charged particles. Electrons carry one kind of charge, usually called negative. Protons carry the opposite kind, usually called positive. These names are historical labels, not moral judgments. There is nothing gloomy or bad about negative charge, and nothing cheerful or noble about positive charge. They are simply two opposite types of electrical behaviour. Two electrons repel each other, two protons repel each other. An electron and a proton attract each other. This simple pattern is one of the great organising rules of nature. It is tempting to imagine that charge is like a tiny hook or handle attached to a particle, something physical you could point to if you had a powerful enough microscope. But charge is stranger than that. It is not a little bump on the surface of an electron. It is not a colour or a texture. It is a built-in property, as basic to an electron as its mass. If you ask what electric charge is made of, physics does not answer by naming smaller parts inside it. Charge is not known as a little machine hidden within the particle. It is one of the things particles simply have, and because they have it, they behave in certain ways. That can feel unsatisfying at first, because the mind wants every explanation to open into a smaller explanation. But in physics, eventually we reach properties that are treated as fundamental. Charge is one of those deep starting points. Still, even if charge itself is fundamental, its effects are everywhere. Imagine two small objects that both have extra electrons. Because electrons repel electrons, the objects push away from each other. They do not need to touch. The influence reaches across the space between them. This is already quite mysterious if we slow down enough to notice it. One object can affect another from a distance. You move one charged thing closer to another, and the other begins to feel a force. No string connects them. No hand reaches out. The space between them is not empty in the simple everyday sense. It is filled with an electric field, an invisible condition created by charge that tells other charges how to move. The field is not just a convenient idea. In modern physics, fields are central. A charge changes the field around it, and another charge responds to that field. This is one reason the universe can build structure. Charged particles do not have to collide like billiard balls to matter to one another. They can sense each other through fields. An electron near a proton feels attraction, because it is in the electric field associated with that proton. Another electron nearby feels repulsion because it is affected by the fields produced by other electrons. At the human scale, these forces are usually hidden inside neutral matter, balanced so neatly that we do not notice them as dramatic pushes and pulls. But at the atomic scale, the electric force is enormous in importance. It is the main reason atoms have their familiar form. It is the reason chemistry exists. It is the reason your hand does not pass through the table. The word neutral is worth pausing over. Many objects around you are electrically neutral overall. That means the positive and negative charges inside them balance. A neutral atom has positively charged protons in its nucleus and negatively charged electrons around it, with the amounts matched so that from far away the atom does not strongly behave as charged. A neutral object may contain a vast number of charged particles, but their effects cancel at larger distances. This is a little like a crowded room where many people are talking softly at once, but from outside the building you hear only a faint murmur. The activity inside is real, but its overall effect is softened. Neutral matter is not matter without charge. It is matter with charge arranged in a balanced way. That distinction is very important for our central question. When we wonder why everything does not explode if electrons repel each other, we might picture all the electrons in an object pushing outward together, like a crowd trying to escape a room. But matter is not just electrons. It also contains positive nuclei, and those nuclei attract electrons. In most ordinary objects, the negative charges and positive charges are deeply interwoven. Electrons push one another apart, but they are also drawn towards nuclei. Nuclei repel other nuclei at short distances, but electrons between atoms can help create attractions. The result is not simple outward pressure from electrons alone. It is a complicated but stable arrangement of opposing influences. A good way to sense electric charge without needing a laboratory is static electricity. Suppose you rub a balloon on hair or wool. In that rubbing, some electrons can be transferred from one material to another. The balloon may end up with extra electrons, while the hair or wool has fewer than before. The balloon is now negatively charged, and because the hairs have been left with a different balance of charge, they may repel one another and stand apart. The balloon can even stick to a wall, not because the wall has suddenly become strongly charged overall, but because the charges within the wall can shift slightly. The negative balloon repels electrons in the wall a little farther away, and leaves the nearer surface slightly more positive in effect. That small rearrangement creates attraction. It is a quiet demonstration that even neutral matter can respond to nearby charge. Static electricity is a gentle doorway into the atomic world. It shows us that electrons can move from place to place in some materials, that imbalance in charge can build up, and that the electric force can act across small distances. But the same rule that lifts hair or sticks a balloon to a wall is also involved in the structure of atoms. The difference is scale and arrangement. In a static shock, charge has been separated enough that we feel a sudden equalizing movement. In ordinary matter, charges are usually arranged in stable patterns. The electric force is still there, but it is not always free to produce visible drama. Lightning is the grand version of the same theme. Inside storm clouds, collisions among ice particles and droplets help separate charge. Different regions of the cloud become charged in different ways, and the ground below can be affected as well. The electric field grows stronger until air, which is normally an insulator, can no longer resist. A path opens, charge rushes, and the sky flashes. Lightning is what happens when charge separation becomes extreme enough that the balance breaks suddenly. It is spectacular, loud, and brief. Ordinary matter is usually the opposite. Its charges are not widely separated into unstable regions. They are arranged locally and continuously, with attractions and repulsions balancing in ways that produce stillness rather than a flash. Inside an atom, the electric attraction between electrons and the nucleus is powerful. If we imagined electrons as tiny classical particles, we might expect them to fall into the nucleus because opposite charges attract, but they do not. The reason, as we will explore more deeply later, is quantum mechanics. Electrons in atoms are not little planets orbiting on neat tracks. They occupy allowed states. They have wave-like behavior. Their arrangement is controlled by rules that prevent the simple collapse our everyday intuition might expect. For now, it is enough to say that electric attraction pulls electrons toward the nucleus, electron repulsion helps keep electrons arranged around one another, and quantum rules decide what arrangements can actually exist. The atom is not a miniature machine held together by one force alone. It is a stable quantum pattern shaped by charge, One of the most surprising things about electric charge is the strength of the electric force compared with gravity. Gravity is the force we notice most easily in daily life because it pulls us toward Earth and gives weight to objects. Drop a pencil and gravity acts plainly. But between individual particles, the electric force is vastly stronger than gravity. The reason gravity dominates our large-scale experience is that mass is always attractive, while electric charge comes in opposite types that often cancel. Earth contains enormous amounts of positive and negative charge, but they balance almost perfectly. Its electric influence from far away is usually tiny, while its gravity accumulates because all mass pulls in the same direction. Atoms are electrically balanced, so planets can be electrically calm. But inside atoms and molecules, where charge separation matters, electricity rules. This helps explain why chemistry is not mostly gravitational. Atoms do not bind into molecules because gravity pulls them together. The gravitational attraction between atoms is far too weak to organize the world of chemistry. It is electric charge, guided by quantum mechanics, that lets atoms interact, share electron arrangements, form bonds, bend into shapes, and create materials. A drop of water, a grain of salt, a strand of protein, a sugar crystal, a leaf, a candle, and a human cell are all built through electromagnetic interactions. Gravity gathers planets and stars. Electric charge shapes the fine structure of matter. Now, if charge is so strong, why does a neutral object not show intense electrical behavior all the time? Because balance can hide strength. Think of two equal teams pulling on a rope in opposite directions. If they are perfectly matched, the rope may barely move, even though the effort is enormous. Neutral matter is filled with positive and negative charges whose fields largely balance at distances we can see. But move very close, into the atomic scale, and the local details matter. An electron near a nucleus feels attraction. An electron near another electron feels repulsion. Atoms approaching one another feel a mixture of forces depending on distance and arrangement. This is why matter can be stable, flexible, hard, soft, sticky, slippery, transparent, opaque, brittle, elastic, or alive. The hidden electrical details produce the visible personalities of materials. Consider a simple piece of salt. It appears as a small white crystal, harmless and quiet. But inside it, there is a strong electrical pattern. Sodium atoms tend to give up an electron, becoming positively charged ions. Chlorine atoms tend to gain an electron, becoming negatively charged ions. The positive and negative ions attract, arranging themselves in a repeated crystal structure. At the same time, ions with the same charge repel, preventing the whole thing from collapsing into a single clump. The crystal exists because attractions and repulsions settle into a stable pattern. Too close, and repulsion becomes strong. Too far, and attraction pulls the ions back. The result is a regular arrangement that can sit calmly in a shaker on a kitchen table. Or think about water. A water molecule is neutral overall, but its charge is not spread evenly. One side has a slightly more negative character, and another side has a slightly more positive character. Because of this uneven charge distribution, water molecules attract one another in particular orientations. This gives water many of its unusual properties, including the way it forms droplets, the way it dissolves salt, and the way ice floats. Again, we see the same lesson. Neutral does not mean electrically inactive. The arrangement of charge matters. Tiny imbalances, shifts, and polarities create real behavior. The electric force also gives us friction, tension, and the feeling of texture. When you slide your fingers over cloth, paper, glass, or stone, you're not simply scraping one solid block against another at a perfectly smooth boundary. At the microscopic level, surfaces are rough, uneven, and full of atoms whose electron clouds interact. The electrons in your skin and the electrons in the surface repel as they come close. Some parts attract slightly because of shifting charge distributions. Bonds may form and break on tiny scales. Your nerves translate these interactions into sensations like smooth, rough, warm, cold, dry, or sticky. The world of touch is an electrical conversation interpreted by biology. Even the act of seeing depends on electric charge. Light interacts with electrons in matter. When light reaches your eye, it triggers changes in molecules in the retina, setting off electrical signals in nerve cells. Those signals travel through your optic nerve and become visual experience in the brain. The colours of objects depend on how their electrons absorb and reflect different kinds of light. A red apple looks red because of how the electrons in its surface materials interact with light from the environment. The apple is not simply painted red by some simple surface label. Its colour is an electromagnetic result. The visible world is, in a very real sense, charge responding to light. Inside your body, electric charge becomes even more intimate. Nerve signals depend on charged atoms moving across cell membranes. Muscles contract because electrical and chemical signals tell fibers when to act. Your heartbeat is coordinated by electrical activity. Every thought, memory, sensation and movement depends on the controlled motion of charged particles in living tissue. This does not mean the brain is just a simple electrical circuit. It is far more complex than that. But charge is part of the language of life. The same basic property that makes electrons repel one another also helps you feel a warm blanket, hear a quiet voice, and decide to close your eyes. So electric charge is both simple and astonishing. Simple because its basic rule can be stated plainly. Same kinds repel, opposite kinds attract. Astonishing because that rule, combined with quantum mechanics and the variety of particles in nature, builds nearly all of ordinary experience. It builds atoms, it shapes molecules, it gives solids their resistance, it lets liquids flow while holding together, it allows gases to press against the walls of a container, it gives chemistry its richness and biology its signalling, it makes lightning possible and keeps your hand from sinking through the chair. The phrase tiny push inside everything is not quite complete, because electric charge also creates pulls. Attraction is just as important as repulsion. But the push between like charges is the part that makes our original question feel so urgent. If electrons repel, why does matter not tear apart? Now we can begin to see why that question needs care. Electrons do repel one another, but they do so inside a world full of positive nuclei, neutral arrangements, shifting fields and quantum restrictions. The repulsion does not act in isolation. It is not a command for matter to explode. It is a contribution to matter having size, spacing, pressure and shape. If you squeeze a sponge, the resistance you feel comes partly from the structure of the material and the air or water inside it. If you squeeze a metal spring, the resistance comes from its shape and the electromagnetic bonds in the metal. If you squeeze an atom, in the loose sense of trying to push atoms closer together, you eventually confront electron repulsion and quantum restrictions very directly. The closer electron clouds are forced together, the more strongly they resist certain kinds of crowding. That resistance is why ordinary matter does not collapse under everyday pressure. It is also why solids push back when you press on them. The world has edges because charges do not pass through one another without consequence. There is another gentle surprise here. Repulsion can help create order. We often think of pushing apart as something that destroys structure, but when many things repel each other while also being confined or attracted by something else, patterns can appear. Put people in a room where they prefer not to stand too close, and they distribute themselves. Put electrons around a nucleus, with attraction drawing them inward and repulsion discouraging them from crowding, and allowed quantum patterns emerge. Put ions in a crystal, with opposites attracting and likes repelling, and a lattice can form. Push and pull together can create arrangement. Nature uses opposition as a building tool. This is why asking what electric charge really means leads us away from the idea of matter as dead stuff. Matter is active even when still. Every object is filled with fields, charges, and restrictions. The calmness we see is not the absence of forces. It is the stability of forces in balance. The table beside you is not quiet because nothing is happening. It is quiet because the happenings are arranged in a way that produces a steady form. Its atoms remain near one another because their electrons and nuclei settle into patterns of attraction and repulsion. Its surface supports objects because electron clouds resist being pushed into other electron clouds. Its shape persists because bonds hold atoms in place while repulsions prevent collapse. When early scientists began to study electricity, they could not see electrons, they saw effects. Amber rubbed with cloth attracted bits of straw. Glass rods and silk produced strange pushes and pulls. Sparks jumped. Compasses moved near wires. Gradually, through patient experiment, people realized that electricity was not a magical fluid in the old sense, but a sign of deeper properties in matter. The discovery of the electron revealed that one kind of charge came in tiny units carried by particles much smaller than atoms. Later, the structure of the atom showed that positive charge lived in the nucleus, while electrons occupied the surrounding region. Each discovery brought the same message into sharper focus. Matter is electrical all the way down into its ordinary structure, but the word ordinary should not make it seem less wonderful. The fact that a neutral object can contain countless charged particles in balance is one of the reasons the world is habitable. If large objects often carried huge net charges, every movement would be dramatic. Walking across a room might become a battle of electrical forces. Instead, matter usually balances charge so closely that we can live among objects without being thrown about by them. Only when charge becomes separated, as in static electricity or lightning, do we notice the force directly. The rest of the time, it remains hidden in structure, like a foundation beneath a house. Now we're ready to take the next step inward. Electric charge gives particles the ability to attract and repel. Electrons repel other electrons, but they're drawn to positive nuclei. These pushes and pulls are carried through electric fields, balanced in neutral matter and shaped by quantum rules. They are strong enough to define the behavior of atoms, yet often hidden enough that a room can feel still. The question is no longer whether electron repulsion exists, it certainly does. The question is how that repulsion becomes part of a stable atom rather than a disaster. To answer that, we have to look more closely at the atom itself, especially at the strange invisible rules that tell electrons where they can be, how they arrange themselves, and why they cannot all simply do the most obvious thing. Now that we have spent a little time with electric charge, we can move closer to the atom itself, because this is where the central puzzle begins to sharpen. Electrons repel one another. That is true. They carry the same kind of electric charge, and when one electron comes near another, each one pushes away from the other. If that were the only fact we knew, atoms would seem impossible. After all, atoms are full of electrons, and matter is full of atoms. If electrons dislike being near electrons, how can atoms have more than one electron at all? Why do they not fling themselves away from one another at once, leaving every atom stripped bare and every object dissolved into a storm of charged particles? The first part of the answer is attraction. Electrons do not exist in atoms as a lonely crowd of negative charge with nothing else around. Every ordinary atom has a nucleus, and that nucleus contains protons which carry the opposite kind of electric charge. Electrons are drawn toward protons. The nucleus acts like a small heavy centre of positive charge, and the electrons are attracted to it. So already we have two tendencies acting together. Electrons repel other electrons, but all of them are attracted toward the nucleus. The atom is not held together by electron friendship. It is held together by the attraction between electrons and the positive nucleus, while electron repulsion shapes how the electrons arrange themselves around that nucleus. That sounds reasonable, but it is still not enough. If we picture electrons as tiny little balls moving around the nucleus, attraction alone creates a different problem. Why did the electrons not simply fall into the nucleus? If a negative particle is attracted to a positive centre, why does it not spiral inward until it crashes? For a long time, this was a serious difficulty. Early pictures of the atom borrowed ideas from familiar motion. People imagined electrons circling the nucleus like planets around the sun. It was an appealing image because it made the atom easy to draw. A little centre, some little dots moving around it, neat paths, simple motion. But nature is not obligated to match our convenient sketches. Electrons are not little planets, and atoms are not tiny solar systems. The difference is crucial. Planets can orbit the sun because gravity pulls them inward, while their motion carries them forward, creating a curved path. But electrically charged particles moving in circles according to classical physics should lose energy. If electrons were little objects orbiting in the ordinary way, they would radiate energy and spiral into the nucleus very quickly. Atoms would not last. Matter would not be stable. The fact that atoms do last tells us that the simple picture must be wrong. The electron is not behaving like a bead on a track, or a moon around a planet, or a speck racing in a miniature circle. Something deeper is happening. That deeper thing is quantum mechanics. It is one of the great turns in the history of physics, and one of the main reasons the world exists in the form we recognize. Quantum mechanics tells us that very small things do not behave like scaled-down versions of everyday objects. An electron is not a tiny hard pellet with a perfectly definite path around the nucleus. It has wave-like behavior. It is described by possibilities, patterns, and allowed states. When we talk about where an electron is in an atom, we're not usually talking about a little dot at one exact point. We're talking about a region where the electron is likely to be found, a kind of spread-out pattern around the nucleus. This can feel strange because our everyday minds are trained by ordinary objects. A marble is here or there, a bird flies along a path, a train follows rails. But an electron in an atom is not like these things. It does not simply sit in one place until it moves to another. It exists in a quantum state, and that state has a shape, an energy, and rules. These states are sometimes called orbitals, though that word can be misleading if it makes us imagine old-fashioned orbits. An orbital is not a path, it is a pattern. It is one of the allowed ways an electron can exist around a nucleus. The word allowed is important. Inside atoms, electrons cannot have just any arrangement they please. Nature permits certain states and not others. This is one of the invisible rules of the atom. The electron does not slowly settle into the nucleus, because there is no allowed stable state corresponding to a tiny electron simply sitting inside the nucleus in the way a small bead might rest in a cup. The electron has a lowest allowed condition, a lowest energy state, and that state still has a spread around the nucleus. It is not infinitely small, it has size. The atom has size partly because electrons cannot be squeezed into arbitrary stillness at the centre. This is one of the quiet miracles of quantum mechanics. It gives atoms a ground floor. Electrons can occupy low energy states, but there is a limit to how low and how compressed their ordinary atomic states can become. Without that, attraction would make atoms collapse. With it, atoms become stable. An electron can be bound to the nucleus, held by attraction, yet not fall all the way in. It can settle into a stable pattern. This is not because it is physically buzzing around like a fly refusing to land. It is because the allowed quantum state itself is extended. The electron is not a classical object trying to decide where to go. It is a quantum object existing according to the structure of its state. Now we can bring electron repulsion back into the story. In an atom with only one electron, such as the simplest form of hydrogen, there is no other electron in that atom for it to repel. The problem is mainly the attraction between the electron and the nucleus, shaped by quantum rules. But most atoms have more than one electron. Helium has 2, carbon has 6, oxygen has 8, iron has many more. In these atoms, the electrons all feel attraction toward the nucleus, but they also repel each other. Each electron is drawn inward by the positive charge of the nucleus and pushed outward or sideways by the presence of other electrons. The result is not a chaotic scramble, because again the quantum rules restrict the possible arrangements. One of the most important of these rules is that electrons cannot all occupy the same exact state in an atom. This rule is known as the Pauli exclusion principle, named after Wolfgang Pauli. Stated gently, it says that certain kinds of particles, including electrons, cannot be identical in every quantum detail while occupying the same system. This rule is not caused by ordinary electrical repulsion. It is deeper and stranger. Even if electrons did not repel electrically, this rule would still prevent them from all piling into the exact same lowest state. It is a quantum rule about the identity of electrons and the structure of their states. This rule is one of the great reasons atoms have shells. Again, shell is a simplified word, but it is useful if we treat it carefully. Electrons fill available states around the nucleus in an ordered way. The lowest available states are filled first, but once they are filled according to the rules, additional electrons must occupy different states. These different states often extend farther from the nucleus or have different shapes. This is why atoms do not simply become smaller and denser as more electrons are added. Extra electrons have to arrange themselves in additional patterns. The atom gains structure. The repulsion between electrons also matters here. Because electrons push each other away, an electron in a many-electron atom does not feel the full pull of the nucleus as if it were alone. Other electrons partly shield it from the positive charge. Inner electrons spend more time close to the nucleus and reduce the effective attraction felt by outer electrons. Outer electrons are held less tightly and are more involved in chemical bonding. This is one reason chemistry has such variety. The electrons farthest from the nucleus, often called valence electrons, are the ones most available for interactions with other atoms. Their arrangement determines whether an atom is eager to give up an electron, gain one, share electron density, or remain relatively unreactive. So electron repulsion is not merely a nuisance inside the atom, it helps shape the atom. It helps decide the sizes of atoms, the energies of electrons, and the way atoms interact. A carbon atom behaves differently from an oxygen atom, not only because oxygen has a larger nucleus, but because its electrons fill and repel and arrange according to these quantum rules. A noble gas resists ordinary chemical bonding because its outer electron arrangement is especially stable. Sodium easily loses an outer electron because that electron is... Atoms can absorb energy, emit light, form bonds, lose electrons, gain electrons, or be ionized if enough energy is supplied. They are not unchangeable, but left alone in ordinary conditions they persist because their electrons occupy allowed states that balance attraction to the nucleus, repulsion from other electrons, and the quantum rule that prevents identical crowding. The atom is stable because its arrangement is not an accident. It is the result of the permitted ways matter can exist. Imagine a set of seats in a quiet theatre, but a very strange theatre where every seat has a different shape and location, and some seats can hold only a certain number of guests. The nucleus is like the reason everyone came into the room. It draws the electrons inward. The electrons would prefer not to be too close to one another because they repel, but they also cannot all choose the very same seat because of the exclusion rule. So they fill the available places according to energy and possibility. That image is not perfect, because electrons are not little people choosing seats, but it gives a useful feeling. The arrangement is constrained. It is not free chaos. This also helps explain why different atoms have different sizes. If electric attraction to the nucleus were the only factor, then atoms with more protons might simply pull their electrons closer and closer. Sometimes a stronger nucleus does pull electrons inward more tightly, but as more electrons are added, they occupy new states and repel one another. Inner electrons shield outer electrons. The balance changes from element to element. This gives the periodic table its rhythm. Atoms grow larger across some steps and smaller across others. They form repeating patterns in their properties, because electron arrangements repeat in broad families. The periodic table is, in a sense, a map of the invisible rules of electrons. Those rules are why matter can have personality. Hydrogen is light and reactive. Helium is calm and unreactive. Carbon forms long chains and complex structures. Oxygen makes combustion possible and helps water have its remarkable character. Sodium reacts dramatically with water. Gold resists corrosion and shines with its familiar colour. These differences are not due to tiny painted labels on atoms. They arise from electron arrangements around nuclei. The electrons determine how atoms meet other atoms. They determine whether matter becomes a gas, a metal, a crystal, a liquid, a mineral, a protein, a membrane, or a living cell. Now let us return to the original worry. If electrons repel, why do they stay in the atom? They stay because the nucleus attracts them, and because the stable arrangement of the atom is not a simple pile of electrons. They are distributed in allowed quantum states. Their repulsion prevents them from crowding too closely in certain ways, but attraction keeps them bound. The atom is like a balanced system in which the inward pull and outward pressure do not erase each other but create structure. Too much simplification makes this seem contradictory, but in the real atom many tendencies can coexist. A person can be drawn toward a warm fire while also not wanting to stand too close to other people around it. The result is a ring of comfortable spacing. The atom is far stranger than that, but the idea of balanced tendencies is helpful. The repulsion between electrons becomes especially important when atoms approach one another. Suppose two atoms move closer. At first, they may attract each other in subtle ways, especially if their electron arrangements can shift or if they can form a chemical bond. But if they are pushed too close, the electrons in one atom begin to strongly repel the electrons in the other. The exclusion rule also becomes important, because electron states from different atoms cannot simply overlap without consequence. The atoms resist being forced into the same space. This resistance is one reason matter feels solid. It is not only electric repulsion in the simple sense, and it is not only the exclusion principle in isolation. It is the combined effect of electron repulsion, quantum state restrictions, and the energy cost of forcing atoms too close together. When your hand rests on a table, the atoms in your skin and the atoms in the table are not merging. Their outer electron regions interact. As they get close, repulsion and quantum restrictions increase sharply. The table pushes back. The nerves in your skin detect pressure. Your brain receives the message, and you experience touch. The boundary feels continuous and solid, but microscopically it is the result of many tiny electromagnetic and quantum interactions. You're not feeling little hard surfaces in the way you might imagine. You're feeling atoms refusing to occupy the same arrangements. This is why the invisibility of the rules matters. You cannot see the exclusion principle. You cannot watch electron orbitals with your eyes. You cannot observe electron repulsion directly as a little pair of hands pushing particles apart. But the effects appear everywhere. The fact that your body has volume, that a spoon has shape, that a crystal has angles, that a gas creates pressure, that metals conduct electricity, that chemical reactions happen in specific ways, all of these are consequences of the hidden rules inside atoms. A gas offers a useful example. In a gas, atoms or molecules move freely compared with a solid or liquid. They fly around, collide with one another, and bounce off the walls of their container. The pressure of the gas comes from those impacts. But what makes the molecules bounce rather than pass through one another? When they come close, their electron regions repel, and their quantum states resist overlapping in forbidden ways. At ordinary temperatures and pressures, molecules remain distinct. They can collide, exchange energy, and move on. The gas does not collapse into a point because the particles have motion, and because their charged and quantum structures resist being forced into the same place. It does not explode unless energy and conditions drive it into rapid expansion or reaction. Again, repulsion contributes to pressure, but pressure alone is not the same as explosion. In a solid, atoms are held near fixed positions, though they still vibrate. The bonds between them arise from electron arrangements that lower the overall energy of the system. But if you try to compress the solid, the atoms are pushed closer than their preferred spacing, and repulsion rises. That is why solids resist compression. A diamond is hard because carbon atoms are bonded in a strong three-dimensional network, with electrons arranged in a way that locks the atoms into a rigid structure. A metal can bend because its atoms are arranged differently, and some electrons are more free to move through the structure. A rubber band stretches because its long molecules uncoil and rearrange, but the bonds and electron interaction still resist and restore shape. In every case, the visible behavior comes from invisible electron rules. Electrons also explain why atoms bond only in certain ways. If atoms were governed merely by attraction between opposite charges and repulsion between like charges, chemistry might be much less specific. But electron states have shapes and capacities. Atoms bond when their electron arrangements can combine into a more stable overall pattern. Sometimes electrons are shared between nuclei. Sometimes one atom gives up an electron and another receives it, creating charged ions that attract. Sometimes neutral molecules attract through slight shifts in charge distribution. But in all cases, electrons do not behave like loose grains of dust. Their allowed states control the possibilities. This is why water has a bent shape, why carbon can form 4 bonds in many compounds, why salt forms crystals, and why proteins fold into complex forms. The idea of allowed states can also help us understand light from atoms. When an atom absorbs energy, an electron can move into a higher allowed state. Later, it may return to a lower state and release light. But the electron cannot release just any amount of energy, because the states are not continuous in the ordinary sense. They are separated by specific gaps. This is why atoms produce characteristic colors of light. Neon signs glow with particular colors. Sodium street lamps shine in a recognizable way. The light from stars carries fingerprints of elements because electrons in atoms absorb and emit light according to their allowed states. Once again, invisible atomic rules become visible at the human scale. There is a calmness in this, even though the subject is strange. Atoms are not stable because they are simple little balls. They are stable because reality has a deep structure. Electrons repel one another, but they are not free to scatter if they are bound by the attraction of a nucleus and arranged in allowed quantum states. They do not collapse into the nucleus because the quantum nature of electrons prevents that classical outcome. They do not all crowd into the same lowest state because the exclusion principle forbids it. They do not make ordinary matter explode because ordinary matter is usually already in a stable or low energy arrangement, with repulsion forming part of that stability rather than undermining it. This also means that the atom is not a tiny battlefield in the sense of constant disorder. It is better understood as a stable pattern sustained by rules. Forces are present, but they are not running wild. The electrons do not need little engines to keep moving, and the nucleus does not need to command them like guards around a castle. The atom is a quantum system. It has states that persist. When undisturbed, those states can remain for long periods. Stability is not maintained by constant repair. It is built into the allowed structure. Of course, atoms can be disrupted. A strong enough electric field can pull electrons away from atoms, creating ions. High-energy radiation can knock electrons into higher states, or remove them entirely. Heat can cause atoms and molecules to move faster and break bonds. Chemical reactions can rearrange electrons between atoms. Nuclear reactions can change the nucleus itself. Matter is stable under some conditions and transformed under others. The point is not that atoms are indestructible. The point is that their ordinary stability is real, and it comes from the combination of electrical attraction, electrical repulsion, and quantum law. This is why the question about electrons repelling each other opens such a wide door. It begins with a simple push and leads into the structure of reality. The electron says no to other electrons in one way, but yes to the attraction of a nucleus in another. It refuses forbidden crowding. It occupies patterns rather than paths. It helps make atoms different from one another. It gives matter its boundaries. It creates the conditions for chemistry. Without electron repulsion, atoms would not have the same sizes or behaviours. Without attraction to nuclei, electrons would not form atoms at all. Without quantum rules, the entire arrangement would fail, so the atom is not an exception to electron repulsion. It is one of the places where electron repulsion is most carefully organised. The invisible rules do not cancel the repulsion, they place it into a structure, they turn it into spacing, shells, chemical behaviour and solidity. When we look at a piece of ordinary matter, we are seeing the peaceful outcome of many such structures repeated beyond counting. A grain of dust contains enormous numbers of atoms, each with electrons arranged according to these rules. A drop of water contains molecules whose electrons hold hydrogen and oxygen together and attract neighbouring molecules in particular ways. A human body contains vast molecular systems whose electrons make life chemistry possible. All of it depends on charged particles not simply doing one thing, but participating in a whole set of rules. And now that the electrons have begun to make more sense, we can turn toward the other side of the atom, the small, heavy centre that makes electron structure possible in the first place. The nucleus is easy to overlook because most of chemistry belongs to electrons, and most of an atom's volume is associated with the electron region. But without the nucleus, there would be no atom to organise. It is the anchor of positive charge, the concentrated mass, the place where protons crowd together despite their own repulsion. That raises another puzzle just as interesting as the first. If protons repel one another because they share the same positive charge, why does the nucleus hold together at all? If electrons give the atom its reach, its softness, its chemistry, and much of the feeling of ordinary matter, then the nucleus gives the atom its weight. It sits at the centre of the story in a way that is easy to miss, because almost everything we touch and taste and smell depends on the outer electrons. Chemistry happens mostly through electrons. The surfaces of things are shaped by electrons. The resistance between your hand and the table comes mostly from electrons refusing to let other electrons crowd too close. But deep inside every atom, far smaller than the spread of the electron cloud, there is a dense central core. It is tiny compared with the atom as a whole, but it contains almost all of the atom's mass. This is the nucleus, the small, heavy anchor at the centre of matter. The nucleus is not just a little bead of positive charge, it is a compact gathering of particles called protons and neutrons. Protons carry positive electric charge. Neutrons carry no electric charge overall. Together they form the central body of the atom. The number of protons in the nucleus determines what element the atom is. 1 proton means hydrogen. 2 protons means helium. 6 protons means carbon. 8 protons means oxygen. Gold, iron, calcium, uranium, and every other element are distinguished by the number of protons in their nuclei. Change that number, and you have changed the identity of the element itself. That fact is worth resting on for a moment. The difference between oxygen and carbon is not a difference in mood or colour or size alone. It is a difference in nuclear identity. The nucleus carries the element's name, so to speak. The electrons determine much of how the atom behaves in chemistry, but the nucleus determines what kind of atom it is. Add or remove electrons and you make an ion. The atom becomes electrically charged, but its elemental identity remains the same. Add or remove neutrons, and you create a different isotope of the same element. The atom may become heavier or lighter, more stable or less stable, but it is still the same element as long as the proton number remains unchanged. Change the number of protons, and the atom crosses a boundary into another element entirely. And yet, the nucleus immediately raises a problem that feels very similar to the one we began with. Protons all carry the same positive charge, like charges repel, so if a nucleus contains more than 1 proton, why does it not fly apart? Why does the helium nucleus with 2 protons stay together? Why does carbon, with 6 protons, exist calmly in the molecules of your body and in the graphite of a pencil? Why does iron, with many protons packed into its nucleus, remain stable enough to form bridges, blood, meteorites, and the cores of planets? If electron repulsion made us wonder why atoms do not burst outward, proton repulsion makes us wonder why nuclei exist at all. The answer is that inside the nucleus there is another force at work, one that does not usually appear in everyday conversation because it acts only across extremely tiny distances. It is called the strong nuclear force. The name is plain, and in this case, very well earned. The strong nuclear force is powerful enough to overcome the electric repulsion between protons when they are very close together. It binds protons and neutrons into nuclei. Without it, the universe would have almost no complex atoms. Hydrogen, with its single proton, could exist, but larger nuclei would be impossible. No carbon, no oxygen, no calcium, no iron, no rocky planets, no water, no chemistry of life as we know it. The strong nuclear force is hidden from ordinary life not because it is weak, but because its range is so short. It is like a firm clasp that works only when particles are already nearly touching. This short range is crucial. Electric forces can reach across large distances, growing weaker as objects separate but still extending outward. Gravity also reaches across vast distances, pulling planets around stars and stars into galaxies. The strong nuclear force does not behave that way at ordinary scales. It is intensely important inside the nucleus, but it fades so quickly beyond that tiny region that you never feel it directly when holding a cup or walking across a room. You feel electromagnetic forces. You feel gravity. You do not feel the strong force between your fingers and a chair because the particles in separate atoms are far too far apart for that force to act between them in the nuclear way. Inside the nucleus, though, distances are small enough for the strong force to dominate. Protons repel each other electrically, but the strong force attracts neighbouring protons and neutrons to one another. Neutrons are especially important in this picture. Since they do not carry electric charge overall, they do not add electric repulsion, but they do participate in the strong nuclear force. In many nuclei, neutrons help add binding without adding more proton repulsion. They act somewhat like extra nuclear glue, though that image is only a rough help. The real force is not glue in the everyday sticky sense. It is one of the fundamental interactions of nature, deeply tied to the quarks inside protons and neutrons and the particles that carry the strong interaction. But at the level of the nucleus, it is fair to say that neutrons help stabilize many nuclei by contributing strong attraction without contributing electric push. The balance between protons and neutrons matters a great deal. A nucleus with too few neutrons may not have enough strong binding to overcome the repulsion among protons. A nucleus with too many neutrons may also become unstable for other reasons. Stable nuclei occupy a kind of narrow valley in the landscape of possibilities. Light elements often have roughly similar numbers of protons and neutrons. Heavier elements need more neutrons than protons, because as the number of protons grows, electric repulsion becomes more serious. More neutrons are needed to help bind the nucleus together. This is one reason the nuclei of heavy elements contain many neutrons. The nucleus is not just a heap of particles, it is a carefully balanced system, and not every combination can last. When a nucleus has an unstable arrangement, it may undergo radioactive decay. This means it changes into a more stable configuration by releasing particles or energy. Some unstable nuclei emit small clusters, some transform a neutron into a proton, or a proton into a neutron through processes involving another fundamental force, the weak nuclear force. Some release energy as radiation. To the atom, this is a nuclear change far deeper than ordinary chemistry. Chemical reactions rearrange electrons among atoms. Nuclear reactions change the nucleus itself. That is why nuclear energy can be so much more intense than chemical energy. The nucleus stores and releases energy on a scale that ordinary electron rearrangements cannot match. This difference between chemical and nuclear processes is important for the question of why matter does not explode. Ordinary matter does not explode because its electrons repel. Ordinary matter remains stable because its atoms and molecules sit in arrangements where electromagnetic forces and quantum rules balance. But inside the nucleus there is a different kind of balance, involving proton repulsion and strong nuclear attraction. If that nuclear balance changes suddenly, the energy involved can be enormous. In a nuclear reactor, in a nuclear weapon, in the heart of a star, or in radioactive decay, changes in nuclei can release energy far beyond everyday chemical reactions. But stable nuclei do not simply fall apart on their own, because their internal arrangements are bound. The protons are not sitting there with no help waiting to scatter. They are held by the strong force. The nucleus is also astonishingly dense. Nearly all the mass of an atom is packed into this tiny centre, while the electron cloud spreads across a much larger region. If an atom were enlarged until the electron cloud reached across a large building, the nucleus would still be like a tiny speck at the centre. That comparison is not exact, but it captures the strangeness. Matter seems solid to us, yet atoms contain vast relative spaces. The reason matter does not feel empty is not because nuclei fill the atom. They do not. It is because electrons and electromagnetic forces define the atom's outer presence. The nucleus provides mass and positive charge, while the electrons provide the atom's size and interactions. Together, they create the familiar substance of the world. This division of roles can be seen in how atoms behave. The nucleus is heavy, compact, and usually well hidden from ordinary chemical events. Electrons are light, spread out, and responsible for most chemical bonding. When atoms form molecules, their nuclei remain mostly intact while electrons rearrange around them. When carbon bonds with oxygen, or hydrogen bonds with oxygen, the nuclei are not merging. They are being held in certain positions by electron arrangements. The nuclei serve as anchors of positive charge, and the electrons form patterns around multiple nuclei. The molecule exists because the electrons can settle into a more stable arrangement around those nuclear centers. So the nucleus anchors matter in two ways. First, it provides the positive charge that attracts electrons and gives atoms their identity. Second, it provides the mass that makes atoms substantial. Without the nucleus, electrons would not form ordinary atoms. Without electrons, nuclei would be bare positive ions, unable to create the full chemistry of matter. The atom is a partnership between a dense center and a diffuse outer structure. The center is tiny and heavy. The outer region is light and extended. One gives identity and weight, the other gives size, bonding and touch. The discovery of the nucleus was one of the great surprises in physics. Before it was understood, some models imagined positive charge spread throughout the atom, with electrons embedded inside it. This seemed reasonable for a time because atoms are neutral overall and very small, but experiments showed that most particles passed through thin metal foil as if the foil were mostly empty, while a few bounced back at sharp angles. This was shocking. It suggested that the atom's positive charge and mass were concentrated in a tiny central region, rather than spread throughout the atom. From this came the nuclear atom. Most of the atom was not filled with solid substance in the ordinary sense. It had a small, dense nucleus and electrons around it. That discovery changed the meaning of matter. A piece of gold no longer seemed like a continuous solid material all the way down. It was a collection of atoms, and each atom was mostly extended electron structure around a tiny nucleus. The fact that some particles bounced back from the foil was like firing pebbles through mist and discovering that hidden inside each misty shape there was a dense stone. It revealed that matter had architecture. It had layers of emptiness, force, and concentrated mass. But if the nucleus is so small, why does it matter so much for the atom? Because the electric attraction between the positive nucleus and the negative electrons sets the stage for electron structure. The number of protons determines how strongly the nucleus attracts electrons. A nucleus with more protons pulls more strongly, though electron shielding and quantum rules complicate the result. This is why atoms change across the periodic table. More protons means a different nuclear charge, which means different electron arrangements, which means different chemistry. The nucleus is not chemically active in the everyday sense. but it quietly controls the number of electrons in a neutral atom and the strength of attraction they feel. Consider carbon. Its nucleus has 6 protons. A neutral carbon atom has 6 electrons. Those electrons arrange themselves in a way that allows carbon to form several bonds, including long chains and rings. This ability makes carbon central to organic chemistry and life. But carbon's chemical richness begins with the identity of its nucleus. 6 protons set the number of electrons. The electrons then follow quantum rules, and from those rules come bonding patterns. The nucleus does not write every detail, but it provides the starting instruction. With a different proton number, the electron arrangement would be different, and the atom would not be carbon. Oxygen, with 8 protons, pulls on its electrons differently and has a different outer electron arrangement. It tends to attract electrons strongly in chemical bonds, which helps make water polar and supports many reactions in living systems. Sodium, with 11 protons, has 1 outer electron that is relatively easy to lose. Chlorine, with 17 protons, tends to gain an electron to reach a more stable arrangement. These behaviors come from electron structure, but electron structure grows around the nucleus. The tiny center sets the identity of the surrounding cloud. The neutron adds another layer of subtlety. Atoms of the same element can have different numbers of neutrons. These are isotopes. Carbon, for example, can exist with different neutron counts. The chemistry remains very similar, because the number of protons and electrons is the same, but the mass and nuclear stability can differ. Some isotopes are stable, others are radioactive. This tells us that the nucleus has its own internal physics, partly independent of the chemical behavior we notice in the outer electrons. 2 atoms may behave almost the same chemically but differ in nuclear stability. One may sit quietly for billions of years, another may decay after a predictable average time, releasing radiation and becoming something else. This is also why radioactive dating works. Certain unstable nuclei decay at steady statistical rates. By measuring the remaining amounts of parent and daughter isotopes in rocks, fossils, or ancient materials, scientists can estimate ages. The clock is not in the electrons, it is in the nucleus. Deep inside matter, nuclear processes keep time in a way that can outlast civilizations. The nucleus is not only an anchor of mass and charge. In some forms, it is a slow clock, ticking through decay across years, centuries, or billions of years. Inside stars, nuclei become the center of another story. Stars shine because nuclear reactions release energy. In the core of a star like the Sun, extreme temperature and pressure allow hydrogen nuclei to overcome their mutual electric repulsion and participate in nuclear fusion. They combine through a series of processes that ultimately build helium and release energy. This is not ordinary burning. A candle burns through chemical reactions involving electrons. A star shines through nuclear reactions involving nuclei. The difference is enormous. The sunlight that warms your face begins with events in the nuclear hearts of atoms, under conditions so extreme that ordinary matter behaves in ways we do not see on Earth's surface. The same electric repulsion that normally keeps protons apart is one reason fusion requires such extreme conditions. 2 positively charged nuclei repel each other. To fuse, they must come close enough for the strong nuclear force to take over. But since the strong force acts only at extremely short range, the nuclei must first overcome the electric barrier that keeps them apart. Stars do this with heat, pressure, and immense numbers of particles moving rapidly in dense cores. Once nuclei get close enough, the strong force can bind them, and energy can be released. In this way, the nucleus is both protected and powerful. It resists casual change, but under the right conditions it can transform and light the cosmos. On Earth, stable nuclei quietly persist. The atoms in a stone may hold nuclei that were forged in ancient stars before the solar system formed. The calcium in bones, the iron in blood, the oxygen in water, the carbon in living tissue. All of these nuclei have histories older than life on Earth. Many were made in stars or stellar explosions, then scattered into space, gathered into new clouds, folded into planets, and eventually arranged into the materials around us. Every nucleus is a tiny anchor not only in matter but in history. It carries the record of cosmic processes that made the elements possible. That history helps make the atom feel less like an isolated object and more like a meeting place of forces. The electrons around an atom determine its immediate relationships. They decide what bonds it can make, what light it can absorb, how it participates in chemistry. The nucleus gives the atom its identity and mass, and it connects the atom to nuclear processes that happen in stars, reactors, and radioactive materials. The atom is therefore both local and cosmic. Its electron cloud touches the world around it. Its nucleus remembers the conditions under which elements are born. Returning to our main puzzle, the nucleus teaches the same lesson in a different language. Like charges repel, but repulsion alone does not decide the outcome. Protons repel one another electrically, yet nuclei exist because the strong nuclear force binds protons and neutrons when they are close enough. Neutrons help stabilize many nuclei by adding strong attraction, without adding electric repulsion. Quantum rules also matter inside the nucleus, because protons and neutrons occupy nuclear states, and not every arrangement is allowed. Stability comes from the full structure, not from one force acting by itself. This is a pattern we keep seeing. Electrons repel, but atoms do not fly apart because electrons are attracted to nuclei and arranged by quantum rules. Protons repel, but nuclei do not usually fly apart because the strong force binds them at tiny distances and neutrons help shape stability. Matter is built not by denying repulsion, but by balancing it with other rules. The universe does not need everything to be attraction. In fact, if everything only attracted, structure would collapse. Repulsion gives spacing. Attraction gives binding. Quantum rules give allowed forms. Together they create stable matter. The nucleus also reminds us that ordinary stability is conditional. Some nuclei are stable under normal conditions, some are unstable and decay, some can split if struck by a neutron or disturbed in the right way, some can fuse under stellar conditions. Stability is not an absolute label that applies everywhere and forever. It depends on the arrangement, the environment, and the available pathways for change. But the stable nuclei that make up most ordinary matter are not on the edge of exploding. They sit in energy arrangements that resist sudden disruption. Their protons may repel, but the binding inside the nucleus is strong enough to hold them. When you hold a pebble, you are holding a collection of atoms whose nuclei contain nearly all the mass. The electrons of those atoms shape the pebble's surface and chemistry. The nuclei give it weight. If you could somehow remove the electrons, the remaining nuclei would no longer form the same object. They would repel electrically if left bare and close together, and the matter would become a plasma-like collection of charged particles. If you could somehow remove the nuclei, the electrons would not form stable ordinary matter by themselves. The pebble exists because nuclei and electrons are arranged together. The nucleus alone is not the object, and the electrons alone are not the object. Matter is the organized relationship between them. The smallness of the nucleus can make it seem remote, but every moment of contact with the world depends on it. The electrons in atoms need nuclei to bind them. The number of protons in nuclei determines which atoms are present. The arrangement of atoms determines the material. The material determines what you see, touch, breathe, and eat. The nucleus may be hidden far inside the atom, but its influence reaches outward through the electron structure it supports. It is like the foundation of a house buried below sight. You do not see it when you enter the room, but the shape of the room depends on it being there. Even your sense of weight is nuclear in a quiet way. Most of the mass of your body is in nuclei. The electrons are essential for chemistry and structure, but they contribute only a small fraction of the mass. When you stand on a scale, most of what gravity pulls on is nuclear mass. The atoms in your bones, muscles, blood, and organs contain nuclei. and those nuclei provide the mass that Earth attracts. The pressure of your feet on the floor then comes from electromagnetic resistance between atoms, mostly electron interactions, so even standing still involves a partnership. Gravity pulls on mass concentrated mostly in nuclei. The floor supports you through electromagnetic forces involving electrons. The ordinary act of standing is a conversation between nuclear mass and electron structure. This is why the atom is such a useful meeting point for physics. It brings together electromagnetism, the strong force, the weak force, quantum mechanics, and gravity in a layered way. Gravity is tiny at the scale of atoms but matters for the mass of large objects. Electromagnetism governs atoms, molecules, and everyday matter. The strong force binds the nucleus. The weak force participates in certain nuclear changes. Quantum mechanics sets the rules for particles in both electrons and nuclei. An atom may seem small, but it contains nearly the whole cast of physical law. The more closely we look, the less matter seems like solid stuff in the old simple sense. It becomes a set of relationships, electrons arranged around nuclei, nuclei built from protons and neutrons made from quarks bound by deeper, strong interactions, fields spreading through space. Forces shaping what can approach, what can bind, what can transform. Yet from all this complexity, the world becomes beautifully dependable. A cup remains on a table, a leaf keeps its shape, a stone has weight, water gathers in droplets. Your body holds together while trillions upon trillions of atoms maintain their tiny balances. The nucleus is therefore not merely the centre of the atom, it is the reason the atom has identity. It is the concentrated store of mass. It is the place where positive charges are held together despite their mutual repulsion. It is a reminder that stability often depends on forces we do not feel directly. We do not sense the strong nuclear force in daily life, but without it, daily life would have no material stage. The air would not contain oxygen as we know it. The ground would not contain silicon, iron, calcium, or aluminum. The chemistry of life would not have carbon. The universe would be far simpler, far emptier in its possibilities. And still, the nucleus is not the whole answer to why matter stays calm. Once the nucleus anchors the atom and attracts electrons, the electrons must still occupy their strange allowed patterns. They must form arrangements that explain why atoms have size, why chemical bonds exist, and why matter resists being squeezed into nothing. The positive centre gives the atom its pull, but the electron world around it gives matter its shape. To understand why electrons do not simply fall inward or fly outward, and why atoms can build molecules rather than collapse or explode, we have to return to the quantum rules that make ordinary intuition less reliable, but nature far more interesting. The atom asks us to give up a very old habit of thought. We're used to imagining small things as tiny versions of large things. A grain of sand is like a rock, only smaller. A droplet is like a pond, only smaller. A marble is like a planet in the loose sense that both are round objects occupying a clear place. So when people first learned that atoms had electrons and nuclei, it was natural to imagine the atom as a tiny mechanical system. A small central nucleus, little electrons circling around it, neat motion, clear paths, something like a miniature solar system hidden inside matter. It is a tidy picture, and for teaching purposes it has had a long life. But the atom is not a miniature solar system. Electrons are not little planets. If they were, ordinary matter would fail almost immediately. The problem begins with attraction. An electron is negatively charged, and the nucleus is positively charged. Opposite charges attract. If the electron were a small object moving around the nucleus in an ordinary circular path, it would not behave like a stable planet. A charged particle moving in such a path should lose energy. It should gradually spiral inward. The atom would collapse. The electron would fall into the nucleus, and the stable atoms needed for chemistry would not exist. Tables, air, water, skin, clouds, wood, and all the quiet objects around us would have no lasting structure. The fact that matter does exist tells us something profound. The everyday mechanical picture is not merely incomplete, it is wrong at the scale of electrons. At the same time, another problem appears if we imagine electrons only as repelling particles. Electrons repel one another, so perhaps we might expect them to fly away from each other and escape the atom. But that does not happen either, not in ordinary stable atoms. The electron is pulled toward the nucleus and repelled by other electrons, yet it does not simply fall inward or scatter outward. It remains part of a stable arrangement. This is where quantum mechanics enters, not as a decorative extra, but as the central reason atoms can exist at all. Quantum mechanics is the physics of things that are very small, though it is more than that. It is the set of rules that describes how particles such as electrons behave when our familiar ideas of position, motion, and path stop working in the usual way. It does not say that electrons are magical, or that anything can happen. Quite the opposite. Quantum mechanics is strict. It gives nature rules that are often less intuitive than the rules of everyday objects, but extremely precise. The atom is stable because electrons obey those rules. A useful first step is to let go of the idea that an electron in an atom follows a little track. When we picture a planet, we can imagine a line through space showing where it travels. At any moment, the planet has a location and a motion. If we had enough information, we could predict its path with great accuracy. An electron in an atom is not like that. It is not usually meaningful to imagine it as a tiny bead moving around the nucleus on a definite route. Instead, the electron is described by a quantum state. That state tells us where the electron is likely to be found if we look, how much energy it has, and what kind of pattern it forms around the nucleus. These patterns are sometimes called orbitals. The word can be troublesome because it sounds like orbit, and orbit makes people think of planets. But an orbital is not a path. It is a region of probability, a standing pattern, an allowed way for an electron to exist around the nucleus. Some orbitals are relatively simple and rounded. Others have more complicated shapes with lobes and directions. The shapes matter because they influence how atoms bond with other atoms. But the most important point for now is that electrons in atoms occupy patterns, not little tracks. The atom is not built from tiny traffic lanes. It is built from allowed quantum states. The word allowed keeps returning because quantum mechanics does something surprising. It limits what can happen. In everyday life, many quantities seem continuous. You can drive a car a little faster or a little slower. You can stand a little nearer or a little farther. You can lift a book to many possible heights, but in atoms, electrons can occupy only certain energy states. They cannot settle into just any condition between them. It is more like a musical instrument than a sliding whistle. A violin string, when held at both ends, can vibrate in certain standing patterns. Not every vibration pattern fits. The length of the string and the conditions at its ends allow some patterns and reject others. In a similar spirit, though not in a perfectly literal way, the electron around a nucleus can exist in certain stable patterns and not in arbitrary ones. This is one reason the electron does not fall into the nucleus. Falling inward in the ordinary sense would mean giving up energy continuously until it reached the centre, but the electron does not have access to a smooth ladder of every possible lower state. There is a lowest allowed state for an electron bound to a nucleus, and that lowest state is not a collapse point. It has a spread. It occupies a region around the nucleus. The electron cannot simply keep shrinking its state forever, because that is not one of the allowed possibilities. The atom has a smallest stable electronic arrangement, not because a tiny electron is physically prevented by a wall, but because the quantum state itself has a structure that cannot be reduced in the ordinary way. There is another way to say this gently. To confine an electron to a very tiny region would give it a very uncertain and energetic motion. Quantum mechanics links how tightly a particle can be localized with how much uncertainty there must be in its motion. If you try to pin the electron down too precisely, the cost is enormous. The electron cannot be made into a perfectly still dot at the center of the atom. The more you try to squeeze its location, the less peaceful its motion becomes. This is not because our instruments are clumsy. It is not merely that we do not know where the electron is, it is that nature itself does not assign the electron the kind of definite classical condition we might want. The atom's size arises partly from this deep quantum limit. So attraction pulls the electron inward, but quantum behavior prevents collapse. The stable atom is the result. This does not mean the electron is fighting the nucleus with little effort like a bird flapping away from a cage. It means the lowest allowed state of the electron has a natural spread around the nucleus. That spread is part of what the atom is. The electron is not failing to fall. It is existing in the state that bound electrons are allowed to occupy. Now add more electrons and the story becomes richer. A helium atom has 2 electrons. Carbon has more. Oxygen has more still. In these atoms, each electron is attracted by the nucleus and repelled by other electrons. If ordinary repulsion were the only rule, the electrons would try to spread out as much as possible while still being pulled toward the nucleus. That already suggests a kind of balance. But quantum mechanics adds another invisible rule, one so important that without it the material world would be unrecognizable. Electrons cannot all occupy the same exact quantum state. This is the exclusion principle. It applies to electrons and to certain other particles. It says, in effect, that 2 electrons in the same atom cannot be identical in every relevant quantum respect. They cannot all crowd into the lowest state as though the atom were a room with unlimited seating in the best chair. Once a state is filled in the permitted way, additional electrons must occupy other states. This rule is not just ordinary electric repulsion. It is deeper than that. Electrons are identical particles, and the mathematical structure of their quantum behavior demands this exclusion. It is one of the hidden laws that makes matter have volume. Without the exclusion principle, atoms would be far smaller, and chemistry would be radically different if it could exist in anything like its known form. Electrons would collapse into the lowest available states around nuclei in ways that would not produce the layered shell structure of atoms. The periodic table would not have its familiar rhythm. Elements would not have the chemical personalities we know. Carbon would not form the same bonds. Oxygen would not behave in the same way. Metals, salts, water, proteins and minerals would lose the underlying electron architecture that gives them their properties. The exclusion principle is not a small correction. It is one of the reasons the world is spacious enough to be a world. This is also one answer to why electrons do not simply fly away. In an atom, electrons are bound by the attraction of the nucleus. To remove an electron requires energy. The electron is not held like a marble glued to a surface, but its quantum state belongs to the atom, and escaping means moving into an unbound state. Some electrons are held more loosely than others, especially outer electrons in larger atoms. That is why atoms can form ions or take part in chemical reactions, but they do not simply leave without cause. Their states are stable unless energy is supplied, or another interaction makes a new arrangement more favourable. The outer electrons of atoms are especially important because they are the ones most involved in bonding. They are farther from the nucleus on average, and more shielded by inner electrons. They can be shared, transferred, or rearranged when atoms come together, but even here, quantum mechanics decides what is possible. Chemical bonds form not because electrons decide to behave socially, but because the combined quantum states of electrons around multiple nuclei can have lower energy than separated atoms. The electrons occupy new patterns that belong to the molecule as a whole. The nuclei are held in place by the balance between attraction to electron density and repulsion from other nuclei. The molecule is stable at a certain arrangement because moving the nuclei too close raises repulsion, while moving them too far loses the bonding advantage. This means that the atom is not a set of separate little parts held in a simple, mechanical balance. It is a quantum system, and molecules are larger quantum systems. The electrons in a molecule may be spread over more than one nucleus. A bond is not a tiny stick between atoms. It is an arrangement of electrons and nuclei that lowers energy and creates a stable relationship. The language of sticks and lines in chemistry diagrams is useful, just as a map is useful, but the real thing is not made of sticks, it is made of quantum states shaped by charge. The same idea helps explain why matter resists being squeezed. If you push atoms closer together, their electron states begin to overlap in ways that become energetically costly. Electrons repel other electrons, and the exclusion principle prevents electrons from simply occupying already filled states. The result is a strong resistance at short distances. This is why your hand does not pass through a table. The atoms in your hand and the atoms in the table cannot simply occupy the same space, because their electrons cannot be forced into the same quantum conditions without a cost. What you feel as solidity is the large-scale effect of these quantum and electromagnetic rules. This resistance can be gentle or extreme depending on the material and the conditions. Soft materials deform because their molecules can shift, bend, slide, or rearrange without breaking all their bonds at once. Hard materials resist because their atoms are locked into strong networks or close-packed structures. Liquids flow because molecules remain close but can move past one another. Gases expand because molecules are far apart and moving freely. In every case, electron behavior is involved. The differences among materials are differences in how electron states create bonds, attractions, repulsions, and allowed motion. A metal, for example, has electrons that are not tied tightly to individual atoms in the same way they are in many other materials. Some electrons can move through the structure more freely, which helps metals conduct electricity and heat. The metal atoms sit in a lattice of positive ions immersed in a sea of mobile electrons, to use a familiar image. This arrangement is stable because the mobile electrons help bind the positive ions together, while also obeying their own quantum rules. The metal can bend because layers of atoms can shift without the structure immediately falling apart. A salt crystal, by contrast, is held by strong attractions between positive and negative ions arranged in a repeated pattern. Push the wrong layers past one another, and like charges may line up, causing the crystal to crack. Different electron and charge arrangements create different kinds of matter. Quantum mechanics also explains why atoms emit and absorb light in particular ways. When an electron in an atom absorbs energy, it can move to a higher allowed state. Later it may return to a lower allowed state and release light. The color of that light depends on the difference between the states. Since the states are specific, the light is specific too. This is why elements have spectral fingerprints. The glow of neon, the yellow light of sodium, the colors seen in fireworks, and the information hidden in starlight all come from electrons moving between allowed states. If electrons could occupy any energy continuously, these fingerprints would blur away. The sharpness of atomic light is evidence of the invisible rules. There is something almost restful about the strictness of it. The quantum world is strange, but it is not sloppy. It does not let electrons do whatever our imagination suggests. They cannot spiral into the nucleus like tiny doomed planets. They cannot all pile into the same state. They cannot take arbitrary energies inside atoms. They cannot be compressed into exact points without consequence. These restrictions might sound limiting, and they are, but they are also creative. They create shells, orbitals, elements, bonding, materials, and life. The atom is stable because nature is selective. This selectivity appears in the periodic table. As protons are added to nuclei and electrons are added around them, the electrons fill available states in an ordered pattern. The outer arrangement repeats in broad ways, which is why elements in the same column often behave similarly. Lithium, sodium, and potassium all have an outer electron arrangement that makes them chemically related. Fluorine, chlorine, and bromine share a different kind of outer tendency. Helium, neon, and argon are especially unreactive because their outer arrangements are filled in stable ways. The periodic table is not just a list, it is a visible form of quantum mechanics. That means the question of why matter does not explode is written into the periodic table itself. The elements exist because electrons occupy stable patterns around nuclei. Chemical reactions happen when those patterns can rearrange into more stable forms. Ordinary objects persist because their atoms and molecules sit in arrangements that do not release energy violently under normal conditions. The repulsion between electrons helps define distances and resistance, but the allowed states give matter its organized variety. Without quantum mechanics, electron repulsion and nuclear attraction would not build the world we see. It may help to compare the atom to sound again, but carefully. A flute can produce certain notes because air inside it supports certain standing waves. A guitar string vibrates in patterns that fit its length and tension. Not every motion becomes a stable note. The instrument selects. The atom is not a musical instrument in the everyday sense, but electrons also form allowed patterns. Stable states are like the notes of matter. The atom cannot play every possible sound. It plays the notes permitted by its structure. Chemistry is what happens when these notes interact, combine, shift, and settle into new harmonies, though we do not need to make that image too musical. The important point is that allowed patterns make stable behavior possible. One reason quantum mechanics feels difficult is that it asks us to accept that probability is not merely ignorance. In ordinary life, if we say there is a chance something is in one place or another, we usually mean we do not know the full facts. The object itself is somewhere definite. A hidden coin is heads or tails even before we look. But in quantum mechanics, the state of an electron is not simply a hidden classical story waiting to be revealed. The probabilities are part of the physical description. When an electron is in an orbital, it is not secretly following a little path while we fail to track it. The orbital is the state. The pattern of probability is real in the sense that it determines what the electron can do and how it interacts. This does not mean the electron is smeared out like butter in a literal everyday way. The language becomes tricky because none of our ordinary images fit perfectly. If we detect an electron, we find it in a particular event. But before detection, its state can be spread out in a way that produces interference and other wave-like effects. The electron is not simply a wave of water, not simply a particle of dust, and not a little planet. It is an electron, and quantum mechanics is the language that correctly describes it. When we use words like wave, particle, cloud, or state, we're building bridges from everyday thought to a world that does not fully resemble everyday objects. For the atom, the result is clear even if the image is difficult. Electrons can be bound without falling. They can repel without scattering. They can occupy regions without having classical paths. They can create stable shells without being miniature planets. They can give matter shape because their states resist forbidden crowding. The strangeness is not optional. It is exactly what makes ordinary reality possible. At very low temperatures, quantum rules can become visible on larger scales. Certain materials become superconductors, allowing electrical current to flow without ordinary resistance. Some atoms can gather into collective quantum states, where many particles behave in a coordinated way. These phenomena remind us that quantum mechanics is not only buried inside atoms, it can rise into the visible world under special conditions, but even at room temperature, even in the quiet ordinary world, quantum rules are already present. Every stable atom is a quantum object. Every chemical bond is quantum in origin. Every solid surface depends on quantum restrictions. You do not have to enter a laboratory to meet quantum mechanics. You meet it whenever your hand rests on a table and does not pass through. The electron's refusal to fall inward is therefore not a mystery left unresolved. It is a sign that the electron is not an ordinary little body. Its lowest bound state around a nucleus has size. The electron's refusal to fly away is also not mysterious once we remember that it's attracted to the nucleus and bound in a state that requires energy to escape. Its refusal to share every detail of a state with another electron gives matter its layered structure. Its electrical repulsion gives atoms and molecules spacing. All of these effects together produce stability. This balance is delicate in one sense and robust in another. It is delicate because changing the rules of quantum mechanics even slightly would change the universe deeply. It is robust because, given the rules we have, atoms are remarkably stable. Hydrogen atoms can last across cosmic time. Carbon atoms can pass through stars, planets, living things, rocks, and air. Oxygen atoms can be part of water, then air, then mineral, then living tissue. The electron arrangements change through chemistry, but the underlying quantum principles remain. Matter transforms without losing the basic rules that let it exist. There is also a useful distinction between being stable and being motionless. Electrons in atoms are not still in the classical sense. The atom is not frozen, but the state can be stable. A standing wave on a string can vibrate without travelling away. A note can persist while the pattern remains. Similarly, an electron state can have energy and structure without the electron spiralling into the nucleus. The atom's stability is not the stillness of a parked car, it is the stability of an allowed pattern. This helps us avoid a common misunderstanding. Sometimes people hear that electrons exist in clouds and imagine a vague, uncertain atom, as if matter is held together by fuzziness. But quantum mechanics is not vague in its predictions. The electron cloud is not a failure to know the real atom. It is the correct form of the atom's description. The patterns can be calculated and tested. The energies match observed light. The bonding explains chemistry. The solidity explains matter. The cloud is not a weakness in the theory. It is the shape of the truth at that scale. As atoms combine into molecules, the same rules keep working. Electrons reorganize around multiple nuclei. Some arrangements lower energy and become stable bonds, others do not. Molecules have shapes because electron states have directional character and because nuclei settle into positions that balance attraction and repulsion. Water is bent. Carbon dioxide is straight. Methane has a three-dimensional arrangement. Proteins fold because countless interactions among charges, electron clouds, and molecular shapes guide them into functional forms. The rules that prevent the electron from falling into the nucleus also allow life to have molecular structure. And this brings us back to the calm room around you. The objects nearby are not exploding because their atoms and molecules are not simply packed with uncontrolled repulsion. They are quantum systems in stable arrangements. Electrons do repel, but their repulsion is part of a larger structure governed by attraction to nuclei, exclusion rules, allowed states, and energy balance. The air is not bursting apart because its molecules are stable, and their motion is ordinary thermal motion, not a runaway release of stored energy. The walls are not flying outward because the atoms in them are bound into materials whose internal forces balance at fixed distances. Your body holds together because its molecules are built from electron arrangements that are stable enough to support life and flexible enough to allow change. If someone asks why electrons do not simply fall into the nucleus, the answer is that electrons are quantum objects with lowest allowed states that have spatial spread. If someone asks why electrons do not simply fly away, the answer is that they are bound by attraction to positive nuclei and need energy to escape. If someone asks why all electrons do not crowd into the same place, the answer is that the exclusion principle forbids identical electrons from sharing the same complete state. If someone asks why matter is solid, the answer is that electron repulsion and quantum restrictions make it energetically costly for atoms to overlap too much. None of these answers alone is the whole story, but together they form the basic explanation. The most remarkable part is that the explanation for everyday solidity is not really everyday at all. It comes from the strange rules of small things. The chair, the floor, the cup, the blanket, and the quiet surface of your own hand all depend on electrons behaving in ways that would have shocked classical physics. Ordinary reality rests on non-ordinary rules. The world feels familiar because those rules are consistent, not because they are intuitive. From here, the next natural question is how these quantum electron arrangements allow atoms to join together. If electrons repel one another, How can atoms form molecules? Why does hydrogen join with oxygen to make water? Why does carbon connect to other carbon atoms in long chains? Why does salt hold together as a crystal? The answer is that chemical bonds are not a denial of repulsion, but a careful arrangement in which electron states around more than one nucleus create stability. Repulsion remains present. Attraction remains present. Quantum rules remain present. The bond forms when the full arrangement is more stable than the separated pieces, and that is how the tiny push inside matter becomes the vast architecture of chemistry. A chemical bond is one of the most familiar invisible things in the world. You never see a bond directly in the way you see a thread tied around a parcel, or a nail holding two boards together, yet bonds are responsible for nearly everything that has shape, smell, taste, texture, strength, softness, flexibility, and life. The paper in a book holds together because atoms are bonded in long molecules. The water in a glass exists because hydrogen and oxygen atoms are bonded into molecules that attract one another. The salt on a table is a crystal because charged atoms arrange in a repeated pattern held by electrical attraction. The proteins in your body fold and function because bonds and weaker molecular attractions guide them into shapes. Even the scent of rain on warm ground comes from molecules whose structures depend on chemical bonds. At first, bonding sounds like the opposite of repulsion. If electrons repel one another, and if the outer parts of atoms are made of electrons, then bringing atoms together should seem difficult. The electron cloud of one atom approaches the electron cloud of another, and the electrons push back. The nuclei also repel other nuclei because protons share positive charge. So why would atoms ever join? Why would matter form molecules, crystals, fibers, metals, liquids, minerals, and living tissue? Why is the universe not just a thin gas of isolated atoms, each keeping a safe distance from every other atom like guests at an awkward gathering? The answer is that chemical bonding is not a simple victory of attraction over repulsion. It is not that repulsion disappears, it does not. Chemical bonding happens when the total arrangement of electrons and nuclei becomes more stable with the atoms together than with them apart. The attraction between electrons and nuclei can lower the energy of the system, while repulsions set limits and establish spacing. If atoms come too close, repulsion becomes too strong and pushes them apart. If atoms remain too far away, the stabilizing attraction is lost. Between those extremes there can be a preferred distance, a stable arrangement where the atoms are held near one another but not collapsed into one another. That preferred distance is what gives a molecule its size, a crystal its pattern, and matter its structure. It is helpful to imagine two atoms approaching slowly. Far apart, they barely notice each other. Their electron clouds are mostly separate. Their nuclei are distant, and each atom behaves almost as if alone. As they come closer, the electrons of one atom begin to feel the positive nucleus of the other atom. This creates attraction. But the electrons also repel the other atom's electrons, and the nuclei repel each other. The full interaction is a mixture of push and pull. At a certain distance, the attractive parts may outweigh the repulsive parts enough to create a stable bond. But if the atoms are forced closer still, repulsion rises sharply. The atoms resist. This is why a bond has a length. Atoms in a molecule are not glued together at no distance. They settle into separation. This is one of the clearest ways repulsion becomes structure. Repulsion does not merely threaten to break things apart. It defines the boundaries of closeness. Without repulsion, atoms attracted to each other might collapse into a much denser state. Without attraction, atoms would not bind at all. With both, matter can have spacing. The distance between atoms in a molecule is not random. It is the point where the competing influences produce a stable arrangement. Structure is born from balance. There are several major kinds of chemical bonding, but they all involve the same broad idea. Electrons and nuclei rearrange so that the system becomes more stable, while repulsion prevents collapse and shapes the final form. The names we give to bonds are useful categories, not separate worlds. Ionic bonds, covalent bonds, metallic bonds, and weaker attractions between molecules can all be understood as different ways charge, electron arrangement, and quantum rules produce stability. An ionic bond is perhaps the easiest to picture at first. Imagine an atom that tends to lose an outer electron, and another atom that tends to gain one. Sodium and chlorine are the classic pair. Sodium has an outer electron that is relatively easy to remove. Chlorine has an electron arrangement that becomes more stable when it gains an extra electron. When sodium gives up an electron to chlorine, sodium becomes positively charged, and chlorine becomes negatively charged. Opposite charges attract. The positive sodium ion and the negative chloride ion pull toward each other. But even here, bonding is not just two little charged balls sticking together. In a salt crystal, each sodium ion is surrounded by several chloride ions, and each chloride ion is surrounded by several sodium ions. The crystal is a repeated arrangement of alternating charges. Positive attracts negative, while positive repels positive and negative repels negative. The stable crystal pattern is the arrangement that balances all these attractions and repulsions across the whole structure. The ions are not simply paired off like dancers holding hands. They form a lattice, a three-dimensional pattern extending through the crystal. The visible grain of salt is the large-scale result of charge arranged in orderly repetition. Repulsion is essential in the salt crystal. It keeps like charges from crowding together. It helps establish the spacing between ions. It also explains why salt crystals can break along flat planes. If a layer is shifted so that like charges are pushed near like charges, repulsion can suddenly dominate and the crystal can split. The brittleness of salt is therefore connected to the same electrical rules that hold it together. The crystal is stable in the right arrangement but vulnerable when that arrangement is disrupted. Covalent bonding is subtler. In a covalent bond, atoms share electrons, though the word share should not be taken too literally, as if electrons were marbles passed politely between children. A covalent bond forms when electrons occupy a quantum state that extends around more than one nucleus. The electron density between the nuclei can attract both positive centers, helping hold the atoms together. The nuclei are pulled toward the shared electron arrangement, while also repelling each other if they get too close. The electrons repel one another too, and quantum rules limit how they can occupy states. The stable bond is the arrangement where all of this produces lower energy than separate atoms. Hydrogen gas gives a simple example. A hydrogen atom has one proton and one electron. When two hydrogen atoms approach, their electrons and nuclei interact. Under the right conditions, the electrons can occupy a combined state associated with both nuclei. This creates a stable hydrogen molecule. The two protons do not collapse into each other because they repel. The two electrons do not collapse into one place because they repel and obey quantum rules. The bond exists because the electron arrangement around both nuclei is more stable than two isolated hydrogen atoms. The molecule is not a pair of atoms tied by a little string. It is a new quantum arrangement. Water is a richer example. Oxygen has a strong attraction for electrons, and hydrogen has one electron to contribute to bonding. In a water molecule, oxygen bonds with two hydrogen atoms. The electrons are not shared equally. Oxygen pulls more strongly on the bonding electron, so the oxygen side of the molecule becomes slightly more negative, while the hydrogen side becomes slightly more positive. The molecule is neutral overall, but its charge is unevenly distributed. This unevenness makes water molecules attract each other. The slightly positive hydrogen side of one molecule is attracted to the slightly negative oxygen side of another. These attractions are weaker than the covalent bonds inside each water molecule, but they are strong enough to give water many of its unusual properties. Here again, repulsion becomes structure. The water molecule has a particular shape, because electron pairs around the oxygen arrange themselves in ways that reduce repulsion while allowing bonding. The molecule is bent rather than straight. That shape gives water its polarity, and water's polarity helps it dissolve salts, form droplets, rise in narrow tubes, and create the environment in which life chemistry operates. The fact that electrons repel one another is part of the reason the molecule has the shape it has. The shape is not a decorative detail. It is essential to water's behaviour. Carbon shows how powerful covalent bonding can become. Carbon atoms can bond with other carbon atoms, forming chains, rings, sheets, and complex frameworks. They can also bond with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and many other elements. This versatility arises from carbon's electron arrangement. Carbon can form stable bonds in several directions, allowing it to build large molecules with detailed shapes. The chemistry of life depends heavily on this. Proteins, sugars, fats, genetic molecules, and countless biological structures rely on carbon frameworks. The quiet fact that carbon's electrons arrange in bond-forming patterns is one reason a living cell can be more than a soup of atoms. But carbon also reminds us that the same element can create very different materials depending on bonding structure. Diamond and graphite are both made of carbon. In diamond, each carbon atom is bonded into a rigid three-dimensional network. This makes diamond extremely hard. In graphite, carbon atoms form flat sheets. The bonds within each sheet are strong, but the sheets can slide past one another more easily. This makes graphite soft enough to leave marks on paper. Same element, different bonding arrangement, completely different material. The difference is not in the identity of the carbon nuclei, but in the structure of the electron bonds between them. Repulsion, attraction, and quantum rules produce architecture, and architecture produces properties. Metallic bonding offers another way for repulsion to become structure. In a metal, many atoms gather in a regular arrangement, and some electrons are not confined to individual atoms. They can move through the material more freely. The positive metal ions are held together by their attraction to this shared sea of mobile electrons. This image is simplified, but useful. The electrons help bind the structure, while also allowing electricity and heat to move through the metal. The positive ions repel one another, but the mobile electrons provide attraction that stabilizes the whole arrangement. The electrons themselves repel, and their quantum behavior controls how they fill available states. The result is a material that can be shiny, conductive, bendable, and strong. This is why a copper wire can carry electric current. Some electrons in the metal can respond to an electric field and drift through the structure. They are not completely free in the sense of moving through empty space without interaction, but compared with electrons in many other materials, they are mobile. The metal's bonding arrangement allows this. A diamond, though made of carbon with strong bonds, does not conduct electricity in the same ordinary way because its electrons are more tightly involved in bonds and not available for easy motion. A material's electrical behavior is a story about electron states. Even weak attractions between molecules depend on charge and electron arrangement. Neutral atoms and molecules can attract one another because their electron clouds are not perfectly rigid. They can shift slightly, creating temporary imbalances in charge. These small fluctuations can induce matching shifts in nearby molecules, producing attraction. These forces are weaker than many chemical bonds, but they matter enormously. They help gases condense into liquids. They help molecules stick to surfaces. They help determine boiling points. They allow geckos to cling to walls through countless tiny interactions between their foot structures and the surfaces they climb. Once again, neutral does not mean inactive. Charges can shift, and even small shifts matter when repeated many times. Hydrogen bonding, which is stronger than many of these weaker attractions but weaker than a typical covalent bond, is especially important in biology. It helps water molecules attract each other. It helps the strands of genetic material recognize and pair. It helps proteins fold into useful shapes. These bonds are not permanent iron locks. They can form and break under ordinary biological conditions, which makes them ideal for living systems. Life needs stability, but not too much. Molecules must hold their shape, but also change, signal, copy, move, and respond. The weaker side of chemical attraction gives biology flexibility. Proteins are excellent examples of structure arising from many kinds of interaction. A protein is a long chain of smaller units, and the chain folds into a specific three-dimensional shape. That shape determines what the protein can do. It may act as an enzyme, a structural support, a signal receiver, or a transporter. The folding depends on attractions and repulsions among different parts of the molecule, interactions with water, hydrogen bonds, ionic attractions, covalent links in some cases, and the tendency of some parts to avoid water. Electron arrangements underlie all of these effects. If the balance is disturbed by heat, acidity, or chemical changes, the protein can unfold or misfold. Cooking an egg is a familiar example of proteins changing structure. The egg white turns from clear and runny to white and firm because heat disrupts the folded protein arrangements and allows new networks to form. In this way, chemical bonding is not only about making molecules, it is about giving matter memory of arrangement. A molecule's properties depend on which atoms are connected and how they are shaped in space. Two molecules can contain the same kinds and numbers of atoms, but be arranged differently, and they can behave very differently. In biology, even left-handed and right-handed versions of molecules can have different effects, because their shapes interact differently with enzymes and receptors. The world of life is highly sensitive to structure, and structure comes from electron rules. Repulsion is present at every step. Electrons repel electrons, and that repulsion influences bond angles, molecular shapes, and the sizes of atoms. Nuclei repel nuclei, preventing atoms from collapsing together. Filled electron states resist overlap, making matter occupy space. In chemistry, atoms do not come together because repulsion has gone away. They come together because attraction creates a stable arrangement at a distance, where repulsion is tolerable and useful. The bond is a compromise that nature can maintain. This compromise can store energy. Chemical reactions happen when bonds break and form, rearranging atoms into new molecules. Breaking a bond requires energy because a stable arrangement must be disrupted. Forming a bond releases energy because a more stable arrangement is created. But a chemical reaction's overall energy depends on the full set of bonds broken and formed, not on one bond alone. Wood burns because molecules in wood and oxygen can rearrange into more stable products, releasing energy as heat and light. A battery works because chemical reactions separate and move charge through a circuit in a controlled way. Digestion releases energy because food molecules are transformed through many steps into lower energy products that the body can use. Chemical energy is energy stored in arrangements of electrons and nuclei. This helps clarify why ordinary matter does not explode even though bonds contain energy. Most chemical bonds are stable under normal conditions. To rearrange them, a reaction pathway must be available, and often an initial input of energy is needed. Paper does not burst into flame at room temperature because its molecules do not easily rearrange with oxygen without a spark or sufficient heat. Gasoline vapor can ignite because its molecules and oxygen can react rapidly once started, releasing energy quickly. Explosions are not caused by the mere presence of electron repulsion. They are caused by rapid rearrangements that release stored energy into heat and expanding gases. Repulsion may help push products apart once energy is released, but the key is the reaction pathway and the energy difference between arrangements. In stable materials, bonds hold atoms in positions where the total energy is low. The atoms vibrate, but they do not spontaneously rearrange into chaos because there is no easy route to a much lower energy state under the conditions present. This is why a wooden chair can remain a chair for years, though it slowly changes through wear, moisture, oxidation, and time. It is why a glass window can sit quietly, though a sharp impact can break it. It is why water remains water until enough heat lets its molecules escape into vapor. Stability is conditional, but it is real. Temperature can be understood as motion and energy among particles. As matter warms, atoms and molecules move and vibrate more vigorously. If enough energy is added, bonds can weaken, structures can melt, molecules can separate or reactions can begin. Ice melts because water molecules gain enough freedom to leave the rigid crystal arrangement while still attracting one another as a liquid. Water boils when molecules gain enough energy to escape into the gas phase. A metal glows when heat gives energy to electrons and atoms in ways that produce light. These changes do not mean the electrical rules have stopped. They mean the balance between energy, motion, attraction, and repulsion has shifted. The solid, liquid, and gas states of matter are therefore chemical and physical stories of bonding and interaction. In a solid, particles are held in a relatively fixed arrangement by bonds or attractions, vibrating around preferred positions. In a liquid, particles remain close but can move past one another. In a gas, particles are far apart and move freely between collisions. Plasma appears when electrons are separated from atoms, creating a gas of charged particles. Each state reflects how strongly particles interact compared with their motion. Electron repulsion helps prevent overlap. Attractions help particles stay together. Thermal energy encourages motion and separation. The visible state is the outcome. Crystals show bonding at its most orderly. Salt, quartz, diamond, ice, and many minerals arrange atoms or ions in repeating patterns. The shapes of crystals reflect the internal arrangement of particles. A snowflake grows as water molecules attach to an ice crystal according to the geometry allowed by their bonding and temperature conditions. Quartz forms hard, transparent crystals because silicon and oxygen atoms bond in a strong network. Metals form crystals too, though their grains may be small and intergrown. The beauty of crystals is not accidental decoration. It is atomic order made visible. Amorphous materials like ordinary glass are different. Their atoms are bonded but not in a long-range repeating pattern. Glass is solid because its atoms are locked into place, but its structure is more disordered than a crystal. This gives it properties distinct from crystalline materials. It can be transparent, brittle, and moldable when hot. Again, the difference lies in arrangement. The same kinds of atomic interactions can produce different behavior depending on whether the structure is ordered or disordered. Bonding also explains why some substances dissolve. When salt dissolves in water, water molecules surround the sodium and chloride ions. The polar water molecules orient themselves so that their partially negative sides face positive ions, and their partially positive sides face negative ions. These attractions can overcome the attractions holding the ions in the crystal, pulling them into solution. The ions are still charged, still interacting, but now their arrangement is different. Dissolving is not disappearance. It is a rearrangement of bonds and attractions. Sugar dissolves differently because sugar molecules are not ions like salt, but they have many parts that can interact favourably with water. Water molecules surround and separate them through attractions involving uneven charge distribution and hydrogen bonding. Oil, by contrast, does not mix well with water because its molecules do not provide the same favourable interactions, and water prefers to maintain its own network of attractions. The familiar separation of oil and water is another expression of molecular structure. It is not stubbornness, it is chemistry. In living cells, chemical bonding becomes dynamic. Molecules do not just sit still. Bonds form and break in controlled sequences. Enzymes help reactions occur at useful rates by positioning molecules, stressing certain bonds, stabilizing transition states, and creating local environments where reactions become easier. The body does not run on tiny explosions but on carefully managed chemical rearrangements. Energy from food is converted into form cells can use. Signals are sent by molecules binding and unbinding. Genetic information is copied by pairing structures that fit together through specific attractions. Muscles move because proteins change shape through chemical and electrical events. Life is not separate from the physics of electrons. It is an intricate use of it. One of the most important ideas here is that bonds are not all equally strong or permanent. Some covalent bonds are strong and require significant energy to break. Ionic attractions in crystals can be strong but depend on the environment. Hydrogen bonds are weaker and can rearrange frequently. Temporary attractions between molecules may be weaker still. This range of bond strengths gives matter versatility. If all bonds were too strong, chemistry would be frozen. If all bonds were too weak, stable structure would vanish. The world needs both durability and change. Bones must support weight, but cells must exchange molecules. DNA must preserve information, but it must also be copied. Water must hold together, but it must also flow. Chemical bonding provides this range. Repulsion is often what gives bonds their shape, rather than merely their existence. In many molecules, electron pairs arrange themselves to reduce repulsion. This affects bond angles. The shape of a molecule affects its polarity, its interactions, its biological function, and its physical properties. A small change in shape can change smell, taste, toxicity, or usefulness. The nose, for example, detects molecules partly through their shapes and interactions with receptors. A molecule smells minty, floral, sulphurous, or smoky because of how its structure interacts with sensory proteins. Those structures trace back to electrons. Even colour can arise from bonding. In many materials, electrons can absorb certain energies of light depending on their molecular or solid structure. The remaining reflected or transmitted light gives colour. Pigments in flowers, dyes in cloth, the green of chlorophyll, the orange of carrots, the dark colour of graphite, the sparkle of gemstones, all depend on how electrons are arranged and how they interact with light. A gemstone's colour may come from trace atoms in a crystal, defects in the structure, or the way the crystal field changes electron states. Beauty, in this sense, is often electronic. Adhesion and cohesion also depend on molecular interactions. Cohesion is the attraction among molecules of the same substance, like water molecules holding together in a droplet. Adhesion is attraction between different substances, like water clinging to glass. These effects shape raindrops, ink on paper, paint on walls, and the way plants draw water upward through narrow vessels. The surface tension of water comes from water molecules attracting one another strongly enough that the surface behaves almost like a stretched skin. Tiny insects can stand on water because their weight is supported by this surface structure. Underneath that delicate scene are charge distributions and hydrogen bonding. Friction, too, is chemical and electrical at heart. Surfaces that seem smooth are rough at microscopic scales. When they slide past each other, their atoms and molecules interact. Tiny contacts form and break. Electron clouds repel. Bonds may temporarily form. Energy is converted into heat. Lubricants work by placing molecules between surfaces that reduce direct contact and allow easier sliding. The difference between squeaking, scraping, gliding, and sticking is a difference in molecular interaction. When you rub your hands together for warmth, the heat comes from mechanical motion being converted into microscopic motion through these interactions. The electrons are still there, shaping what contact means. A bond is therefore not a little object, it is a stable relationship. That may sound almost philosophical, but it is physically precise in spirit. The atoms in a molecule are held because the whole arrangement has a lower energy than separated parts. The electrons occupy states that belong to the arrangement. Repulsion prevents overcompression. Attraction prevents drifting apart. Quantum rules decide what states are possible. The result is a specific geometry with specific behaviour. This is why diagrams can both help and mislead. In chemistry, we draw lines between atoms to represent bonds. Those lines are useful. They let us track structure and reactions. But the line is not a tiny bar in nature. It represents an electron arrangement, a distribution of charge and quantum state. When a bond breaks, no little stick snaps. Instead, electron arrangements change. When a bond forms, no hook catches. Instead, a new stable state appears for the system. The drawing is a map, not the territory. Understanding this also makes the original question less alarming. If electrons repel each other, why does everything not explode? because the same repulsion that might seem destructive is one of the ingredients that create stable distances and shapes. In chemical bonds, atoms are held not at zero separation, but at bond lengths. In crystals, ions form patterns because repulsion keeps like charges apart while attraction brings opposites together. In molecules, electron repulsion influences geometry and prevents collapse. In solids, repulsion and exclusion make compression difficult. The push is not an enemy of structure, it is one of structure's tools. The world around you is built from these tools. Wood is made largely from long organic molecules and complex cellular structures, held by covalent bonds and many weaker interactions. Glass is a network of bonded atoms lacking a regular crystal pattern. Metal is positive ions in a sea of mobile electrons. Salt is an ionic lattice. Water is polar molecules attracting and releasing one another constantly. Air is a mixture of molecules that collide and move freely. Your body is built from molecules that bond strongly where they must, weakly where they need flexibility, and selectively where information must be recognized. Every ordinary object can be read as a history of bonds. A ceramic bowl has atoms locked into a hard network through high heat. A piece of bread has starches, proteins, water, gases, and browned surface molecules formed by heat-driven reactions. A leaf has cellulose fibers, pigments, water, proteins, sugars, minerals, and membranes. A candle has wax molecules that can react with oxygen when heated enough. A battery has materials arranged so chemical reactions can drive charge through a circuit. The variety of objects is the variety of bonding, and yet, bonding is still rooted in the atom's central balance. Electrons are attracted to nuclei. Electrons repel electrons. Nuclei repel nuclei. Quantum rules restrict states. Chemical bonds are the arrangements that survive these conditions and lower energy. Nothing in bonding requires electrons to stop repelling. They continue to repel. But when atoms come together in the right way, electron states can spread, shift, pair, transfer, or delocalize so that the whole system becomes stable. The repulsion becomes part of the geometry. It tells atoms how close is too close. It gives molecules shape. It gives materials resistance. As we follow this idea outward from individual bonds to larger pieces of matter, the next question becomes more practical. How do these countless tiny arrangements create the world of solid things? Why does a table hold its shape? Why does your body not collapse through a chair? Why does a stone feel hard, a pillow soft, a metal spoon cool, and a rubber band stretchy? The answer is that chemical bonds and electron repulsion scale upward. When repeated across enormous numbers of atoms, they create solids, liquids, gases, tissues, metals, crystals, planets, and stars. The same invisible rules that hold a water molecule together help explain why the world feels stable under your hand. By the time atoms have become molecules, crystals, metals, fibers, fluids, and living tissue, the original question has changed shape. It began as a worry about electrons repelling each other, a tiny push that seemed as though it should make matter fly apart. But now we can see that the push is not simply destructive. It gives atoms boundaries. It helps set bond lengths. It keeps electron clouds from being squeezed into the same space. It shapes the angles of molecules, the spacing of crystals, and the resistance of solids. It is part of the reason matter has form. The next step is to understand how this form becomes the stable world around us, the world of tables, bodies, rocks, pillows, metals, planets, and even stars. The stability of the everyday world is easy to underestimate because it is so constant. A table does not appear to be performing a physical achievement when it holds up a cup. A floor does not seem miraculous when it supports your weight. Your body does not feel like an arrangement of forces negotiating with gravity every second. Ordinary things look still, and stillness can trick the mind into thinking nothing is happening. But at the atomic scale, stillness is never emptiness. A solid object is a vast crowd of atoms or molecules held in place by bonds and interactions, each one vibrating, each one surrounded by electron clouds, each one participating in the balance between attraction and repulsion. The table is not calm because its atoms are inactive. It is calm because their activity is organized. When you place a cup on a table, gravity pulls the cup downward. The cup presses on the table. At the point of contact, atoms in the bottom of the cup are pushed slightly closer to atoms in the tabletop. Their electron clouds begin to resist being compressed into one another. Chemical bonds in the table stretch and bend by tiny amounts. The material deforms, though usually far too little for your eye to notice. The table pushes back. This upward push is not a separate magical support force. It is the collective result of electromagnetic interactions and quantum restrictions among atoms. The electrons in the atoms of the table resist the electrons in the atoms of the cup. The bonds inside the table resist distortion. The whole structure settles into a balance where the downward pull of gravity is matched by the upward resistance of matter. This is what it means for a table to hold something. It is not that the table has a hard essence that refuses motion. It is that its atoms are bonded into a structure that can slightly deform and push back. A wooden table does this differently from a metal table or a plastic table. Wood is made of cellular structures and long organic molecules. Metal is made of atoms arranged with mobile electrons that allow layers to shift while remaining bonded. Plastic is made of long molecular chains that can tangle, flex, and resist. The details differ, but the principle is the same. Atoms are held together by electromagnetic and quantum rules, and when they are compressed or stretched, those rules produce restoring forces. The word solid can make matter sound absolute, but solidity is a range of behaviour. Some solids are hard, some soft, some brittle, some elastic, some bend easily, some shatter, some flow very slowly under stress, some return to shape, and some permanently deform. These differences come from bonding and structure. In a crystal such as diamond, carbon atoms are locked into a strong three-dimensional network. If you try to press into diamond, the bonds resist strongly. The electron arrangements do not allow easy rearrangement, so the material is hard. In graphite, also made of carbon, atoms are bonded strongly within sheets, but the sheets can slide over one another. That makes graphite soft enough to write with. Same element, very different structure, very different stability under force. A metal feels stable in another way. It may be strong, but it can often bend without breaking. This is because metallic bonding allows atoms to shift position, while the mobile electrons continue to help hold the structure together. The positive metal ions can slide past one another more easily than ions in a brittle salt crystal, because the bonding is less directional. If you bend a copper wire, you're not breaking every bond at once. You're allowing parts of the atomic arrangement to shift while the electron sea maintains cohesion. The wire changes shape, but it does not explode, crumble, or dissolve, because the bonding structure permits deformation. Ceramics and salts often behave differently. In an ionic crystal, positive and negative ions are arranged in a repeating pattern. In the correct arrangement, opposite charges attract and the crystal is stable. But if layers shift so that like charges come close, repulsion can dominate and the material can crack. This is why some crystals are brittle. They may be strong against compression but weak against certain kinds of shear. The structure is stable until it is forced into an unfavourable arrangement, and then repulsion helps drive fracture. The breaking of a solid is not a failure of physics, it is physics following the consequences of structure. Soft materials show a different kind of atomic order. A pillow, a sponge, a piece of rubber, or a muscle does not resist pressure the way diamond does. A pillow compresses because its fibres bend, air moves through gaps, and its internal structure rearranges. Rubber stretches because its long molecular chains straighten and shift under tension, then tend to curl back when released. Your body is full of materials that are stable but flexible. Skin stretches, tendons pull, bones support, cartilage cushions, muscles contract. None of these materials could work if matter were only rigid. Life depends on stability that can move. This is an important point. Stability is not the same as stiffness. A living body is stable because its molecules and tissues maintain organized relationships while constantly changing. Cells exchange ions, proteins fold and unfold, membranes flex, blood flows, bones remodel over time, muscles consume chemical energy to generate motion. The atoms in your body do not remain fixed forever in the same positions, yet the body as a whole persists. It is stable dynamically. It holds a pattern through controlled change. The same electromagnetic and quantum rules that allow a crystal to remain rigid also allow a cell membrane to remain flexible, a protein to find its shape, and a nerve cell to send a signal. When you stand on the ground, the stability of your body and the stability of the ground meet. Gravity pulls your body downward. The ground pushes upward through electron repulsion and structural resistance. The bones in your feet and legs compress slightly. The floor compresses slightly. The atoms in both systems shift minutely until forces balance. You do not notice the tiny deformation because it is usually very small, but it is there. Every step is a negotiation among gravity, muscle action, friction, elasticity, and atomic resistance. Walking feels simple because your nervous system handles the coordination, and matter handles the support. Friction is part of this support. Without friction, your feet would slide helplessly. Friction comes from the microscopic interactions between surfaces. Even smooth surfaces are rough at small scales. Tiny high points touch, electron clouds repel, molecular attractions form and break, and energy is converted into heat. The sole of a shoe grips the floor because its material deforms around surface irregularities and because molecular interactions resist sliding. Ice is slippery partly because conditions at its surface can allow easier motion, and because the interactions between shoe and ice differ from those between shoe and dry ground. Friction is not a mysterious surface property added after matter exists. It is matter interacting through the same atomic rules. Liquids feel less stable than solids because they do not hold a fixed shape, but they are stable in their own way. Water in a glass does not fly apart because water molecules attract one another. They are not locked into fixed positions as in ice, but they remain close, continually moving, rotating, forming and breaking temporary attractions. The surface of water has tension because molecules at the surface are pulled inward by neighbouring molecules. A droplet forms because cohesion pulls water into a compact shape, while thermal motion keeps the molecules moving. Water can flow because the attractions are strong enough to hold it together, but weak enough to allow rearrangement. Gases are more spread out, but they too are stable under ordinary conditions. The air around you is made mostly of molecules moving rapidly in all directions. They collide with one another and with surfaces. They do not settle to the floor as a thin layer because their thermal motion keeps them distributed, while gravity still affects the atmosphere as a whole. The pressure of air comes from countless molecular impacts. A balloon inflates because gas molecules strike its inner surface, stretching the rubber until the inward elastic force balances the gas pressure. If the balloon bursts, it is not because electrons suddenly decided to repel more strongly. It is because the stretched material can no longer contain the pressure, and the gas expands rapidly through the opening. Pressure is a useful bridge between the microscopic and the visible. In a gas, pressure comes from moving particles colliding with walls. In a liquid, pressure comes from weight, molecular motion, and the resistance of molecules to compression. In a solid, stress and pressure are carried through bonds and electron cloud interactions. At the human scale, pressure feels like a push. At the atomic scale, it is the outcome of motion, repulsion, attraction, and structure. When you squeeze a closed plastic bottle, you compress the air inside, deform the plastic, and increase the collisions and restoring forces within the system. The bottle pushes back because its molecules do not allow arbitrary compression. The deeper you push into matter, the stronger this resistance can become. Ordinary solids and liquids are hard to compress because atoms already occupy preferred distances. Push them closer, and electron repulsion and quantum exclusion grow more important. The atoms resist overlapping. This resistance explains why matter has volume. It also explains why planets can support mountains and why rocks can hold shape under gravity, though not without limit. Deep inside a planet, pressure becomes enormous. Atoms are squeezed into denser arrangements. Minerals change phase. Electrons may behave differently under extreme compression. The matter remains stable, but the form of stability changes with pressure. Earth itself is a grand example of matter under layered conditions. At the surface, rocks are solid, water flows, air moves, and living things build delicate structures. Deeper down, rock can deform slowly over long times, flowing like an extremely thick material in the mantle. Deeper still, iron and other elements exist under immense pressure and heat in the core, with parts liquid and parts solid depending on the balance of temperature and pressure. The stability of Earth is not one kind of stability. It is many, arranged by depth. Chemical bonds, metallic behavior, heat, gravity, and pressure all cooperate in different ways. Gravity becomes more important as we move from tables and bodies to planets and stars. In everyday objects, electromagnetic forces dominate structure. Gravity pulls, but it is weak between individual atoms. However, gravity always attracts and adds up over large amounts of mass. A planet forms because gravity gathers matter. But once matter is gathered, it does not collapse into a point because electromagnetic and quantum forces resist compression. The atoms and molecules in rock, ice, metal, and gas push back. The planet settles into a balance between gravity pulling inward and matter resisting inward compression. This balance is called hydrostatic equilibrium in stars and large planets, though we do not need the term to understand the idea. Gravity pulls everything inward. Pressure pushes outward. The pressure may come from heat, from moving particles, from radiation, or from quantum effects depending on the object. A stable star exists when inward gravity and outward pressure balance. A planet exists when gravity has gathered matter into a rounded body but not crushed it beyond the resistance its matter can provide. Again, stability is not stillness without force, it is force matched by force. Stars take this story into more extreme territory. A star is a huge sphere of hot plasma, where atoms are stripped of many electrons and matter is ionized. Electrons and nuclei move freely in a dense, hot environment. Gravity tries to crush the star inward. Thermal pressure from the hot particles pushes outward. In the core, nuclear fusion releases energy, replacing the heat that escapes from the surface as light. A star like the Sun is stable for a long time because these processes balance. Gravity compresses the core enough for fusion to occur. Fusion produces energy that maintains pressure. Pressure resists gravity. The star shines. The Sun does not explode outward under ordinary conditions because the outward pressure is balanced by gravity. It does not collapse inward because pressure and fusion support it. Its stability is dynamic, not static. Energy is constantly produced in the core and carried outward. Light escapes into space. Gravity constantly pulls inward. The star remains stable because the rates and forces adjust. If the core cools slightly, gravity compresses it, raising temperature and increasing fusion. If the core heats too much, pressure expands it, reducing the fusion rate. This self-regulation allows stars to live for millions or billions of years depending on their mass. Inside the Sun, electron repulsion is part of the plasma's behavior, but it is not the whole story. At such high temperatures, electrons are not bound to individual atoms in the ordinary way. Matter becomes a soup of charged particles. The particles repel and attract electromagnetically, collide, exchange energy, and respond to fields. The nuclei, positively charged, repel one another strongly, which makes fusion difficult. They must get extremely close before the strong nuclear force can bind them. The star's heat and pressure make that possible. In this case, repulsion helps delay fusion, making stars burn steadily rather than all at once. If nuclei fuse too easily, stars would not last long enough to provide stable light for planets. More massive stars live faster because their cores are hotter and denser. They fuse fuel more rapidly, shine more intensely, and end their lives sooner. When the balance between gravity and pressure changes near the end of a star's life, dramatic events can occur. Some stars shed outer layers, some collapse into dense remnants, some explode as supernovae. These explosions are not caused by ordinary electron repulsion alone. They come from the failure and transformation of the star's internal support, nuclear processes, gravity, and shock waves. The stability of a star can last for ages, but when its energy sources and pressure supports change, the balance can break catastrophically. White dwarf stars reveal electron behavior in one of its most powerful forms. A white dwarf is the dense remnant left behind by certain stars after they exhaust their nuclear fuel and shed outer layers. It has roughly the mass of a star packed into a volume comparable to a planet. Ordinary atoms cannot exist there in the normal way. Matter is crushed so densely that electrons are forced into extreme quantum conditions. The exclusion principle becomes the main source of pressure resisting further collapse. Electrons cannot all occupy the same states, and this creates a pressure even when the star is no longer producing heat by fusion. This electron degeneracy pressure, to use the scientific name, can support the white dwarf against gravity up to a limit. That is a remarkable extension of the same rule that helps make ordinary matter occupy space. The exclusion principle that keeps electrons in atoms from all crowding into the same state also helps hold up a dead star. In your chair, electron behavior contributes to solidity. In a white dwarf, electron behavior supports something with stellar mass. The scale is different beyond imagination, but the principle is connected. Quantum mechanics is not just a small world curiosity. Under the right conditions, it shapes astronomical objects. If a white dwarf gains too much mass, electron pressure can no longer support it. The balance fails, and depending on the circumstances, it may undergo runaway nuclear burning or collapse further. In even denser stellar remnants such as neutron stars, electrons and protons can combine under immense pressure, and matter becomes dominated by neutrons. Neutron degeneracy pressure and nuclear forces then resist gravity. A neutron star is so dense that a small amount of its matter would have extraordinary mass by ordinary standards. Here again, stability is a balance between gravity, trying to crush matter, and quantum and nuclear forces resisting. Black holes represent the case where known forms of pressure cannot halt collapse beyond a certain point. Once enough mass is compressed into a small enough region, gravity creates an event horizon. The details of what happens at the deepest interior remain among the great questions of physics, involving the unresolved relationship between general relativity and quantum mechanics. But for our present story, black holes are a reminder that stability has limits. Matter can resist compression through electromagnetic forces, quantum exclusion, nuclear forces and pressure, but under extreme enough gravity, those supports can be overcome. At ordinary scales, however, matter is comfortably far from such extremes. A table is not close to becoming a black hole. A human body is not near nuclear collapse. A rock is stable because its atoms and bonds are in low energy arrangements, and the pressures acting on it are within the range its structure can resist. We live in a middle world, far from the tiny nucleus and far from the crushing gravity of stellar remnants, but dependent on both kinds of physics. Our matter is stable because atoms are stable. Our planet is stable because matter resists gravity. Our sun is stable because gravity and pressure balance while nuclear fusion proceeds steadily. The stability of the world is therefore layered. At the smallest ordinary chemical scale, electrons occupy quantum states around nuclei. Atoms bind into molecules or solids through electron arrangements. Materials gain properties from the structure of their bonds. Objects hold shape because enormous numbers of atoms resist displacement collectively. Planets hold together because gravity gathers matter while pressure resists compression. Stars shine because gravity, heat, plasma, and nuclear reactions balance. At each level, forces that might seem opposed become part of a stable pattern. This is why nothing explodes simply because electrons repel. Repulsion is already included in the stable arrangement. It is not waiting outside the system like a delayed catastrophe. In a solid, electron repulsion helps define how close atoms can get. In a molecule, it helps define shape. In a gas, it contributes to collisions and pressure. In a star, charged particle repulsion shapes plasma behavior and makes nuclear fusion require special conditions. If conditions change enough, matter can transform violently, but ordinary stability is real because the forces are balanced at every scale. The human body is perhaps the most intimate example. It is soft enough to breathe, move, heal, and sense, yet stable enough to maintain form. Bones contain mineral crystals and collagen fibers arranged to resist stress. Muscles contain protein structures that slide and pull using chemical energy. Cell membranes are flexible barriers made of molecules that arrange themselves because one part interacts favorably with water, while another avoids it. Nerve signals depend on charged ions moving through channels. Blood carries oxygen using molecules shaped by bonds around iron atoms. Every part of the body is built from charged particles and electron arrangements. But the body does not explode because those arrangements are controlled, layered, and constantly regulated. Even the pressure inside cells is balanced. Water tends to move across membranes. Ions create electrical and chemical gradients. Proteins and pumps maintain differences between inside and outside. Too much imbalance can harm a cell, but living systems use these imbalances carefully. They store energy in gradients, send signals through voltage changes, and use molecular machines powered by chemical reactions. Life is stable not by eliminating tension, but by managing it. That is very much in the spirit of matter itself. Stability often comes from controlled imbalance, not from the absence of force. A simple chair supporting a sleeping cat may seem far removed from stars and quantum mechanics, but it belongs to the same universe of balances. The chair's material resists bending because of bonds between atoms. The cat's body is supported by bones and tissues made of molecules. Gravity pulls both downward, the floor pushes upward. Electrons in surfaces repel as contact points compress. Chemical bonds stretch slightly. Heat moves slowly between bodies. Air molecules collide with everything. The scene looks still, but it is filled with invisible motion and balance. Nothing explodes because every relevant force has found its ordinary place. When a system does explode, it is usually because stored energy has a rapid path outward. A firecracker contains chemicals that can rearrange quickly into hot gases. The gases expand, pressure rises, and the casing breaks. A volcanic eruption happens when gas-rich magma under pressure finds a path to the surface. A supernova happens when a star's internal balance fails in a catastrophic way. These events require special conditions. They are not the everyday consequence of charged particles repelling. Electron repulsion may contribute to pressure in many systems, but explosion requires a sudden imbalance and energy release. The calmness of matter is therefore not fragile in the way the original question might suggest. It is not as though every object is barely preventing electrons from launching away. Instead, matter is built from stable states. Electrons are bound to nuclei in atoms. Atoms are bound into molecules and solids, where energy is lower than in separated arrangements. Repulsion helps set spacing and prevents collapse. Quantum rules prevent forbidden crowding. Materials resist forces according to their structures. The universe is not balancing on a knife edge in every coffee cup. It is full of robust arrangements, though all arrangements can change under the right conditions. This robustness is why science can work at all. If atoms change their behavior unpredictably from moment to moment, there would be no stable chemistry, no reliable materials, no repeatable experiments. But atoms of the same element behave consistently because their nuclei and electrons follow the same rules. Oxygen atoms bond in recognizable ways. Carbon atoms form familiar structures. Water has dependable properties. Iron can be forged. Silicon can be made into electronics. Biology can repeat molecular processes. The stability of matter gives the world memory and repeatability. Still, stable does not mean eternal. A table decays. A body ages. A mountain erodes. A star exhausts its fuel. Bonds break and form. Atoms move through cycles of air, water, rock, and life. Stability exists over timescales. Some arrangements last fractions of a second. Some last millions of years. Some nuclei may remain unchanged for times longer than the age of the universe as we know it. Others decay quickly. The world is a mixture of temporary and long-lasting structures. What matters is that at each scale, there are rules that allow patterns to persist. The original phrase, "everything explodes," imagines a universe where repulsion wins instantly and completely. But the real universe is more patient. It uses repulsion to create distance, attraction to create binding, and quantum laws to create allowed forms. It uses pressure to resist gravity, gravity to gather matter, heat to drive change, and bonds to store structure. Stability is not a single fact. It is a layered achievement. So when you look at a table, you are seeing more than wood or metal or plastic. You're seeing atoms prevented from collapsing by quantum rules, held together by electron arrangements, shaped by chemical bonds, and supported against gravity by electromagnetic resistance. When you look at your hand, you're seeing living matter built from molecules whose shapes and interactions depend on the electrons. When you look at the night sky, you're seeing stars held in balance by gravity and pressure, shining because nuclei can transform under extreme conditions. From the table to the body to the star, matter remains stable, because nature has many ways to arrange push and pull into form. And with that, the journey begins to turn toward its final balance. We have followed electrons from their tiny repulsion into atomic structure, into nuclei, into quantum rules, into chemical bonds, and outward into solids, bodies, planets, and stars. The answer has never been that repulsion is absent. It has been that repulsion is woven into the architecture. The last step is to gather these ideas into one clear picture of why the universe does not tear itself apart, why it does not collapse into a point, and why the world can remain calm enough for a cup to sit on a table, a person to rest under a blanket, and atoms to quietly keep their agreements while the night moves on. At the heart of this question is a small misunderstanding that is very easy to make. When we hear that electrons repel one another, we may imagine repulsion as a kind of rebellion, a force that always wants to scatter matter outward until nothing remains but a thin mist of particles. It sounds like a simple rule with a dramatic consequence. Electrons push other electrons away. Matter is full of electrons, therefore matter should fly apart. But nature rarely builds the world from one rule acting alone. The world is not the result of a single force shouting in an empty room. It is the result of many rules speaking at once, sometimes opposing, sometimes reinforcing, often balancing so neatly that the result looks like stillness. The calmness of ordinary matter is not the absence of forces, it is the presence of forces in stable arrangement. This is one of the most important ideas in all of physics, and it is also one of the easiest to miss because stable things look uneventful. A stone on the ground seems inactive, a cup on a table seems ordinary, a sleeping cat on a blanket seems as far from deep physics as anything can be. But each of these is filled with charged particles, quantum rules, molecular bonds, vibrations, attractions, repulsions, pressures, and tiny adjustments. Nothing about matter is truly idle. It is just organized well enough that its restless interior becomes a steady exterior. Electrons do repel one another. That fact remains true from beginning to end. If two electrons are brought close together, they push apart because they carry the same kind of electric charge. This repulsion helps make matter occupy space. It helps prevent electron clouds from simply merging. It helps create resistance when atoms are pressed together. It contributes to the feeling of solidity when your hand touches a desk or when your feet rest on the floor. In that sense, electron repulsion is not a threat to the world. It is one of the reasons the world has surfaces. It is one of the reasons objects can push back, but electrons are not alone. Every ordinary atom has a nucleus, and the nucleus contains positively charged protons. Electrons are attracted to that positive center. This attraction is what binds electrons to atoms in the first place. If there were only repulsion between electrons, atoms could not exist as we know them. If there were only attraction between electrons and nuclei with no quantum restrictions, atoms would collapse. But nature has both attraction and repulsion, and it has quantum rules that decide what arrangements are possible. The atom is stable because the electron is drawn inward, yet cannot simply fall into the nucleus as a tiny classical object would. It occupies allowed quantum states, patterns that have size and structure. That word pattern is perhaps one of the gentlest ways to understand the atom. The electron is not a tiny planet in a neat orbit. It is not a bead sliding on an invisible wire. It exists in a quantum state, a pattern of probability and energy around the nucleus. Some patterns are allowed, others are not. The lowest stable pattern is not a point at the center, it is spread around the nucleus. This is why the electron does not simply fall inward. The atom has a natural size because the electron's quantum state cannot be compressed into nothing without consequence. When there is more than one electron, another rule becomes vital. Electrons cannot all occupy the same exact quantum state. This exclusion rule gives matter its layered structure. It helps produce the shell-like organization of atoms. It helps explain the periodic table. It helps determine why carbon behaves like carbon, why oxygen behaves like oxygen, why sodium and chlorine can form salt, why noble gases are quiet and reluctant, and why the world has chemical variety. This rule is not ordinary electrical repulsion, though both matter. Electrical repulsion keeps electrons from liking close company in the usual charge sense. The exclusion rule prevents identical electrons from all crowding into the same quantum condition. Together, they give matter volume, order, and resistance. The nucleus has its own balance. Protons repel one another because they are all positively charged, and yet nuclei do not usually fly apart. They're held by the strong nuclear force, which acts only across extremely tiny distances, but is powerful enough to bind protons and neutrons together when they are close. Neutrons help many nuclei remain stable because they add nuclear binding without adding electric repulsion. So even at the atom's center, the lesson repeats. Repulsion is real, but it does not rule alone. A stronger, shorter-range attraction binds the nucleus. Too few or too many neutrons can make a nucleus unstable. Some nuclei decay, some can split, some can fuse under extreme conditions. But stable nuclei persist because their inner forces are arranged in a lasting way. This is why matter is layered in its stability. The nucleus is held by nuclear forces. The electrons are bound by electromagnetic attraction to the nucleus and organized by quantum rules. Atoms join into molecules when electron arrangements around multiple nuclei lower the total energy. Molecules gather into liquids and solids through bonds and weaker attractions. Solids resist compression because atoms cannot be pushed arbitrarily close together. Planets resist gravitational collapse because matter has pressure and structure. Stars resist collapse because heat, radiation, plasma pressure, nuclear reactions, and sometimes quantum effects push outward against gravity. At every scale, reality is a negotiation. A chemical bond is one of the clearest examples of this negotiation. Atoms do not bond because all repulsion disappears. They bond because attraction and repulsion create a stable distance. If two atoms are too far apart, they barely interact. If they come to a suitable distance, their electrons and nuclei can settle into a lower energy arrangement. If they are forced too close, electron repulsion and nuclear repulsion rise sharply, pushing them apart. The bond is not a tiny stick, it is a stable relationship. It exists because the whole arrangement works better than the separated parts. Repulsion gives the bond its limits. Attraction gives the bond its hold. In an ionic crystal like salt, positive and negative ions attract, while like charges repel. The crystal forms a repeated pattern because that arrangement lets attractions dominate while keeping like charges properly separated. In a covalent molecule, electrons occupy states associated with more than one nucleus, allowing the nuclei to be held near each other. In metals, mobile electrons help bind positive ions into structures that can conduct electricity, and often bend without breaking. In water, uneven charge distribution creates attractions between molecules that shape droplets. Ice, boiling, dissolving, and life chemistry. Every material is a different answer to the same question. How can charged particles arrange themselves so that the result is stable? That is what makes the idea of everything exploding so misleading. An explosion is not what happens whenever repulsion exists. An explosion happens when stored energy is released very quickly and has a path to expand outward. A firecracker explodes because chemical reactions rapidly produce hot gases. A balloon bursts because stretched material can no longer contain internal pressure. A star explodes when its deep internal balance fails under extreme conditions. Ordinary matter is not usually in such a state. Its atoms and molecules have already settled into arrangements that do not suddenly release energy. The electron repulsion inside matter is not a coiled disaster waiting for permission. It is part of the settled structure. A table holds its shape because its atoms are bonded into a material that resists deformation. Press down on it, and its atoms shift slightly. Electron clouds resist being pushed into one another. Bonds stretch or compress by tiny amounts. The table pushes back. Your hand feels that push as firmness. The table is not infinitely rigid. It can bend, crack, burn, rot, melt, or break under the right conditions. But under ordinary conditions, its internal forces are stable enough to make it a table. The same is true of a chair, a wall, a stone, a book, a pillow, or a window. Each is a balance of microscopic rules appearing as macroscopic reliability. Your body is another form of the same architecture, but more dynamic. A human body is not stable like a crystal locked in place. It is stable like a living process. Molecules form membranes, proteins, bones, blood, nerves, and tissues. Chemical bonds hold structures together, while weaker interactions allow flexibility. Ions move through channels, electrical signals travel along nerves, muscles contract through molecular changes, cells repair, divide, respond, and communicate. The body is full of charges and gradients, but it does not fly apart because those charges are controlled and arranged. Life does not avoid physics. Life uses physics with extraordinary care. Even thought depends on charged matter. Nerve cells maintain differences in charged particles across their membranes. Signals move because these differences change in controlled waves. Muscles respond, senses arise, memories form, and attention drifts because charged atoms and molecules move according to physical rules. The same kind of electric charge that makes electrons repel one another is involved in the quiet fact that you can hear these words. Imagine an atom, feel your own breathing, and become aware of the surface beneath you. At the scale of planets, gravity joins the story more visibly. Gravity pulls matter inward. Electromagnetic forces and quantum rules resist compression. A planet becomes round because gravity gathers matter, but it does not collapse into a point because matter pushes back. Rock, metal, ice, and gas each resist in their own way. Deep inside a planet, pressure changes the structure of matter. Minerals transform. Metals flow or solidify depending on temperature and pressure. The surface world may look calm, but the planet beneath it is another balance, held between inward gravity and the resistance of matter. Stars are still more dramatic. A star exists because gravity gathers gas until the core becomes hot and dense enough for nuclear fusion. Gravity pulls inward. Heat and pressure push outward. Fusion releases energy that helps maintain the pressure. The star does not explode immediately because the outward push is balanced by gravity. It does not collapse immediately because pressure supports it. Its life is a long adjustment between inward and outward tendencies. When the balance changes at the end of a star's life, the result can be gentle or violent depending on the star's mass and structure. A white dwarf can be held up by the quantum resistance of electrons. A neutron star can be supported by even denser nuclear and quantum effects. A black hole forms when gravity overwhelms all known supports. The universe contains many kinds of balance, and also many ways for balance to fail. Yet the fact that balance can fail does not make stability less real. A bridge can collapse, but that does not mean bridges are illusions. A candle can burn, but that does not mean wax is always exploding. A star can die, but that does not mean stars are unstable in the ordinary sense. Stability always belongs to conditions and timescales. Matter is stable enough for atoms to form, stars to shine, planets to cool, oceans to gather, chemistry to grow complex, and life to arise. The calm architecture of reality is not eternal in every detail, but it is durable enough to build a universe with history. This is perhaps the most important conclusion. Reality is not held together because everything is pulling together. It is held together because pulling and pushing are both needed. Attraction alone would be disastrous. If electrons simply fell into nuclei, atoms would collapse. If protons simply attracted without limits, nuclei would behave differently. If gravity acted without any form of pressure or quantum resistance, matter would crush inward. Repulsion alone would also be disastrous. Electrons would scatter. Protons would refuse nuclei. Atoms would not bind. Molecules would not form. The world exists because attraction and repulsion create distances, boundaries, shapes, and tensions that can last. A useful way to think about this is to imagine the world as a set of preferred separations. Atoms in a molecule prefer certain distances because closer is too repulsive and farther loses attraction. Ions in a crystal prefer certain positions because the arrangement balances many charges at once. Molecules in a liquid remain close but mobile because attractions are strong enough to gather them and weak enough to let them move. Solids resist compression because their atoms already occupy positions shaped by bonds and electron rules. Stars maintain size because gravity and pressure find a temporary balance. Structure is not just what matter is made of. Structure is where matter is allowed to be. This is why the ordinary world feels so dependable. The atoms in your room are not deciding from moment to moment whether to exist. They are in stable states. The molecules in your walls are not constantly on the verge of flying apart. They occupy arrangements that would require energy to disrupt. The air molecules around you move rapidly, but they remain molecules unless enough energy breaks them apart. The water in a glass can evaporate slowly, freeze, boil, or react under certain conditions, but it does not randomly become a fireball. Matter follows pathways. It changes when conditions provide a route. It does not change merely because one ingredient inside it involves repulsion. Repulsion, in fact, is often what lets matter be useful. Without electron repulsion and quantum exclusion, your hand could not press against anything. Surfaces would not feel solid. Tools could not hold shape. Bones could not support weight. Air could not exert pressure in the familiar way. Atoms could not maintain size. A world without repulsion would not be a peaceful world of perfect attraction. It would be a collapsed world, or perhaps no ordinary world at all. The push is part of the gift. Attraction is also essential. Without attraction, electrons would not bind to nuclei. Atoms would not form. Chemical bonds would not hold. Liquids would not gather. Solids would not remain coherent. Gravity would not collect matter into planets and stars. A world without attraction would be dispersed and empty of lasting form. The pull is also part of the gift. The universe becomes rich because it has both. Quantum mechanics adds the rulebook that makes these forces build rather than merely fight. It tells electrons what states they may occupy. It prevents identical electrons from crowding into the same condition. It gives atoms discrete structures and elements repeating patterns. It turns what might have been a simple cloud of charged particles into the periodic table, chemistry, materials, and life. If attraction and repulsion are the push and pull of reality, quantum mechanics is the hidden grammar that makes those forces speak in meaningful sentences. The strong nuclear force adds another layer, binding the nucleus against the repulsion of protons. Without it, there would be no complex nuclei, no carbon, no oxygen, no iron, no calcium. The weak nuclear force allows certain transformations in nuclei and plays a role in stars and radioactive decay. Gravity gathers the large-scale universe and sets the stage for stars and planets. Electromagnetism shapes atoms, bonds, light, electricity, touch, chemistry, and biology. Each force has its domain, and the world we know appears where their effects overlap in stable ways. So the answer to the original question can be stated plainly, though the path to it is rich. Everything does not explode because electron repulsion is balanced by attraction to positive nuclei, shaped by quantum rules, and incorporated into stable arrangements of atoms and molecules. Matter remains solid because electrons and nuclei settle into structures where energy is low and compression is resisted. Nuclei remain together because the strong nuclear force overcomes proton repulsion at tiny distances. Objects remain intact because chemical bonds and material structures distribute forces. Planets and stars remain stable when pressure balances gravity. Explosions happen only when a system has stored energy and a rapid pathway for release. Repulsion alone is not enough. But there is a softer way to say it too. Matter is calm because nature has learned, through its laws, how to arrange disagreement. Electrons push one another away, but nuclei call them inward. Protons push one another apart, but the strong force binds them close. Atoms resist overlap, but they can bond at the right distance. Molecules jostle, but they can gather. Gravity compresses, but pressure applies. The world is not peaceful because every part wants the same thing. It is peaceful because the opposing tendencies have found forms that endure. Look again, in your imagination, at the nearest ordinary object. A cup, a pillow, a phone, a blanket, a wall, a sleeve, a book, a patch of floor. It seems simple because it belongs to daily life, but inside it, electrons are arranged around nuclei. Nuclei are held together by nuclear forces. Atoms are bonded into molecules or solids. Electron repulsion gives the object volume. Chemical bonds give it structure. Quantum rules give it stability. Gravity gives it weight. Electromagnetic resistance gives it touch. The object is not merely sitting there. It is being held in existence by a layered agreement among the laws of physics. And here you are too, made of the same kind of agreement. The atoms in your body were formed through cosmic processes, gathered into Earth, cycled through air and water and food, arranged into cells, tissues, thoughts, and breath. The electrons in your atoms repel other electrons, yet those repulsions help give your body boundaries. The nuclei in your atoms contain protons that repel, yet nuclear forces hold them. The molecules in your cells are stable enough to make you, but flexible enough to let you live. You are not separate from the calm architecture of reality. You are one of its most intricate examples. This makes the original question feel less like a problem and more like an invitation. If electrons repel each other, why does anything stay together? Because the universe is not built from sameness. It is built from balance. It uses attraction and repulsion together. It uses rules that prevent collapse and rules that prevent escape. It creates stable distances, preferred arrangements, layered structures, and temporary forms that can last long enough to matter. The quiet world around you is not quiet because it is simple. It is quiet because its complexity has become steady. So the next time your hand rests on a table, or your head sinks into a pillow, or you lift a cup of tea and feel its warmth through the surface, you might remember that you are encountering the result of invisible negotiations. Your hand does not pass through the cup because electrons resist overlap. The cup does not fall apart because its atoms are bonded. The atoms do not collapse because electrons obey quantum rules. The nuclei do not burst apart because the strong force holds them. The warmth you feel is the motion of particles. The light by which you see is an electromagnetic wave interacting with electrons. The whole moment, quiet as it seems, is physics in balance. And if that thought feels large, let it be large in a restful way. Nothing about it asks you to solve the universe tonight. It is enough to notice that the world is more delicately arranged than it appears, and more reliable than it has any right to seem at first glance. The same forces that could sound like a recipe for chaos are the forces that make stillness possible. The tiny push between electrons is part of the reason matter has shape. The pull between opposite charges is part of the reason atoms bind. The strictness of quantum rules is part of the reason chemistry can exist. The strength of the nucleus is part of the reason elements survive. The balance between gravity and pressure is part of the reason stars shine long enough to warm planets. In the end, everything does not explode because reality is not a pile of particles left unattended. It is an architecture of allowed relationships. It is a universe where closeness has limits, distance has consequences, and stability appears between too much pull and too much push. The world rests in that middle ground. A table beneath a lamp, a body beneath a blanket, a planet beneath a sky, and stars burning far away in the dark are all expressions of the same deep principle: attraction gathers. Repulsion spaces. Quantum rules organize, forces balance, matter remains. And now, after following this question from the tiny charge of an electron to the quiet stability of solid things and the burning lives of stars, we can return to the room around us. The object nearest to you is still there. The floor still supports you. The air still holds its gentle pressure. The atoms in your body are still keeping their agreements. Nothing needed to explode for the universe to be interesting. It was already interesting in its calmness. So if this slow journey through the hidden architecture of matter has made the world feel a little stranger, a little steadier, or perhaps a little softer around the edges, then let that be a pleasant place to rest. The electrons may keep repelling one another. The nuclei may keep anchoring the atoms. The bonds may keep holding the shapes of things together, and you may simply breathe, settle, and let the balanced world continue quietly around you.